All right. So welcome to How to Inspect the Attic Insulation, Ventilation, and Interior. Again, I'm Dan Rossi. I'll be your host for tonight, and we're gonna jump right into this material here. All right. All right, guys. So here's a couple like standards of practice, right? What the inspector shall inspect, right? Any unfinished spaces, including attics, crawl spaces, foundation areas, ventilation of unfinished spaces, including attic, crawl spaces, any unfinished foundation areas, and mechanical exhaust systems in the kitchen, bathrooms, and laundry rooms. All right. The inspector shall describe the type of insulation that's observed, right? The approximate average depth of the insulation and the unfinished areas, floor and roof surface. And if the inspector shall report as in need of any correction of those areas with missing insulation or ventilation present. What we're not required to inspect. Okay. So we're not required to enter the attic or any unfinished spaces that are not readily accessible, where entry could cause damage, or in the inspector's opinion, that's a safety hazard. We're not going to be moving, touching, or disturbing any insulation or vapor retarders. Break or otherwise damage the surface, finish, or weather seal on any access panels or covers. We're not there to identify the composition or the R value of insulation material. We're not going to activate any thermostatically operated fans. We're not going to determine the types of materials used in insulation or wrapping pipes, ducts, jackets, boilers, or wiring, or determine the adequacy of ventilation. Doors, windows, and interiors. So the inspector shall open and close a relative representative number of doors and windows, right? Take a look at floors, walls, ceilings, stairs, steps, landings, stairways, ramps, railings, guardrails, handrails, any garage vehicle doors, and operation of garage vehicle door openers using normal operating controls. The inspector shall describe a garage vehicle door as manual operated or installed with a garage door opener. The inspector shall report as in need of any corrections, improper spacing between balusters, spindles, rails for steps, stairways, guards, and railings. The photoelectric safety sensors on your garage doors, we should be testing them, and any windows that are obviously fogged or have any other evidence of broken seals. Inspector is not required to inspect paint, wallpaper, window treatments, finish treatments, inspect floor coverings or carpeting, inspect any central vacuum systems, safety glazing, inspect security systems or any low voltage components, evaluate the fastening of islands, countertops, cabinets, sink tops, or fixtures, move furniture, or stored items or any coverings such as carpets or rugs in order to inspect the concealed floor structure, move suspended ceiling tiles, inspect or move any household appliances, inspect or operate equipment housed in the garage except as otherwise noted, verify or certify the proper operation of any pressure activated auto reverse or related safety features of a garage door. Operate or evaluate any security bar release and opening mechanisms, whether interior or exterior, including their compliance with local, state, or federal standards. Operate any system, appliance, or component that requires the use of a code or a lock. Discover firewall compromises. Okay, inspect pools, spas, or fountains. Determine the adequacy of a whirlpool or spa jets, water force, or bubbles. Determine the structural integrity or leakage of pools or spas. All right, so jumping into heat and energy, right? So heat and energy and insulation are all related to each other, okay? So they go hand in hand. One important reason we need to understand how heat moves is because warm air is going to hold moisture, all right? And warm air and moist air needs to be controlled in relations to your building envelope. Uncontrolled movement of warm air moisture can cause a lot of problems. Heat needs to be controlled to keep the occupancy of the home comfortable. When a home is well insulated, obviously you're going to save on energy costs. All right. There are essentially three ways that heat moves from one area to another. When bodies of unequal temperatures are near each other, heat leaves one body and goes to the other. Heat moves from the hotter body, and the colder body will absorb it. The greater the difference in temperature, the greater the rate of flow of heat will happen. All right. Heat moves from one body to another in the following ways. So radiation, obviously you can see there, convection, and then conduction. So radiation is the transfer of heat energy by electromagnetic wave. Heat is transferred in direct rays. It travels in a straight line from the source of the heat to the body, similar to the sun, right? The closer you are to the object, the warmer you're going to feel. The intensity of the heat radiated from the hot object decreases as your distance from the object increases. You'll feel cool in a room that has a cold floor, walls, and ceiling. The amount of heat loss from your body in the room depends on the relative temperature of the objects in that room. The colder the floor is, the relative to the temperature of your feet, the greater the heat loss from your body will be as you continue to stand there. If the floor, walls, and ceiling of that room are relatively warmer than your body, then the heat will be radiated to your body from those objects or surfaces. Radiant heat emits in all directions. Radiant heating in residential buildings include the piping and electrical wiring in the floors, walls, and ceilings. Reflective materials are commonly used in a radiant heat emitting system in order to direct or control where that heat is emitted. Conduction. All right, so conduction is transfer of heat from one molecule to another or through one substance to another. It is heat that moves from one body to another by direct contact. For example, heat is transferred by conduction from a boiler heat exchanger to the water passing through it. When the air conditioning is operating properly, the liquid line should feel warm to the touch and the suction line will feel cold. Heat is a form of energy, and when that heat comes in contact with matter, it makes the atoms and molecules move. When the molecules move, they collide with others, making them move to. Um, this movement transfers heat through the matter. Convection. All right. Convection is understood by most people by the phrase heat rises. Convection is the transfer of heat by warming the air next to a hot surface and then moving that warm air. It's transfer of heat by the motion of heated matter itself. The air moves from one place to another, carrying heat along with it. Since warm air is lighter than um, cool air will obviously fall, warm air will rise. Warm fluids tend to rise while the surrounding cool fluids fall. The rising and falling motion tends to form loops or convective loops where warm air rises and cool air falls. When a certain amount of air is heated up, it expands and takes up more space. In other words, hot air is less dense than cold air. Any substance that is less dense than the fluid of its surrounding will float. Hot air floats on cold air because it's less dense, just as a piece of wood will float in dense because water is more dense. Warm air is often described as weighing less than cool air. Warm air rises and cool air falls. Inside a wall cavity, there will be convective loops where cool and warm air moving through the wall cavity. If warm, moist air comes into contact with a cold surface of that wall assembly, that's when condensation will form. As another example, an old gravity furnace heats the air and the air gets lighter and it rises through the building. All right, so moisture movement. So, water vapor may move in three different ways: through air transportation, diffusion through materials, and thermal diffusion. Of these three air movement accounts for more than 98% of all water vapor movement in building activities. The illustration shows here water vapor, right? Movement by diffusion and air transport. Air naturally moves from air pressure areas to lower pressure areas by the easiest path, generally through any available hole or crack in a building envelope. Moisture transfers by air currents happens very quickly and carefully and permittedly air sealing any unintended paths for air movement in and out of the house is a very effective moisture control strategy. Right, as an inspector, we want to call out anytime we see an opening, an unsealed wall protrusion in those areas. The other two driving forces, right, diffusion through materials and heat transfer are much a slower process. than air transportation. The most common building materials slow moisture diffusion to a large degree, although they never stop it completely. Insulation also helps reduce heat flow or transfer. The problem is that there are ways to control vapor diffusion that are ineffective at controlling air transported moisture, and vice versa. An effectively built wall is designed to control both vapor diffusion and air transportation at the same time in relation to the climate of your house's location. So everything's going to look different if you live in the Northeast versus if you live in the Southeast. All right, so vapor diffusion is how moisture in a vapor state moves through a material because of a difference in pressure, known as the pressure gradient, or a difference in temperature, known as thermal gradient. Vapor diffusion is not air movement. Vapor diffusion is water vapor moving through a material from a high pressure to a low pressure, or from the warm side of a wall to the cool side of a wall. Moisture in air will move from high pressure to low pressure or from high temperature to low temperature. Only if that air is moving contains water vapor. Thermal or heat diffusion happens when moisture in a vapor state moves from warm air of an assembly to the cold part. The second law of thermodynamics explains how water vapor or moisture can be pressure and thermally driven from high or hot or low. Diffusions is an important factor to understand, but diffusion is also a slow process. Air, however, can move and flow quickly and in large volumes. Air transportation accounts for more than 98% of all vapor movement in building cavities. Okay. Air naturally moves from a high pressure area to a low one by the easiest path possible, generally through, again, any cracks in the building envelope. Moisture transfers by air currents is very fast, in the range of several hundred cubic feet of air per minute. Thus, to control the movement, a house should have any untended airways or pathways sealed. Diffusion through materials is a much slower process. The most common building materials that slow the moisture diffusion to a large degree, then it can't stop it though. I'm sorry, excuse me. The illustration shows a wall that has a hole in it. All right. So when you have a hole in one piece of 4x8 gypsum, that hole, that's a 1 inch hole, will allow up to 30 quarts of water to travel through a heating season. Right. As an inspector, we want to verify and confirm that or notate that these areas are there so they can be addressed by our clients. The illustration shows a wall, right? We talked about that. The law of physics govern how most air reacts with various temperature conditions. The study of moist air properties is technically referred to psychometrics. A psychometric chart is used by professionals to determine at what temperature and moisture concentration water vapor begins to condense. The temperature and moist concentration at which water vapor begins to condense is the dew point. By understanding how to find the dew point, you will better understand how to inspect for and diagnose moisture problems in a house. We're not right there to check dew points and go through all that, but it's a good thing to understand so that you can better understand maybe what is going on if you're finding condensation or moisture damage in areas. Relative humidity, all right, refers to the amount of moisture contained in the quantity of air compared to the maximum amount of moisture the air could hold at the same temperature. As warm air, its ability to hold water vapor increases. So the hotter it gets, the more humid it can get. The capacity decreases as the air cools. For example, according to the chart, air at 68 degrees or 20 degrees Celsius with 0.216 ounces of water vapor per pound of air versus the same air at 59 degrees holds about 28% more moisture. The moisture that air can no longer hold condenses on the first cold surface it encounters. That's the dew point. If this surface is within an exterior wall cavity, that's when you're getting it wet, damp insulation and the framing behind it. In addition to air movement, temperature and moisture content can also be controlled. Since insulation reduces heat transfer or flow, it also moderates the effect of temperature across the building's cavity, envelope cavity. In most US climates, properly installed vapor diffusion retarders can be used to reduce the amount of moisture transfer, except in deliberately ventilated spaces such as attics, crawl spaces, areas, unconditioned areas. Work together to reduce, these will work together to reduce the opportunity for condensation to form inside the house's ceilings, walls, and floors. All right, so moisture, right? That's the enemy of all homes. Okay. So you could see here we have a summer and here you have a winter. So when moist air touches a cold surface, some of the moisture may leave the air and condense or become a liquid. If the moisture condenses inside a wall cavity or in the accessible attic, you may not be able to see the water, but it will start causing numerous problems. When a wall is insulated, the temperature of the space inside the wall is changed. A surface inside that wall, such as the plywood sheathing behind the siding, can become much colder in the wintertime than it was before than it was before the wall was insulated. This cold surface could be the place where moisture traveling through the wall could condense and cause trouble. Same situation can happen in the attic. So in the attic, when you see that dark staining on the roof structure, rusted nails, all any staining on the framing members, like that's an indication that the air that is up there is condensing on those building materials, and that's going to cause obviously damage to those building materials. As an inspector, we should obviously be calling those out. All right. So protection from water damage. All right. Water may be essential to life, right? We all need water to live, but as destructive force, water can diminish the value of your client's home or building. As an inspector, we're required to report any condition or clear indications of active water penetration. All right, so the following are common building related sources of intrusion. As you can see, windows and doors, right? Check for leaks around all windows and doors and storefront systems in any commercial buildings that you guys are doing. The roof, so improper drainage systems, roofs that are sloping, reduce the roof's life. And become a primary source of moisture intrusion. Leaks are also common around vents, right? Your plumbing stacks, your fixed roof exhaust vents, and any rooftop air conditioning units. Other specialized equipment in buildings. A lot of now we're seeing a lot of solar, so you're seeing a lot of conduit going through roof penetrations, sometimes the service masts, skylights. So we're looking around all those items in the roof. The foundation and exterior wall, you want to make sure all cracks or holes in exterior walls, joints, and foundations are all secured, right, with sealant of some sort to prevent any moisture intrusion. The plumbing, you want to check for any plumbing leaks, fixtures, dripping pipes, fire sprinkler systems in commercial buildings, any clogged drains. A lot of times the condensate drains get clogged up, they back into the drain pan. Right, you want to make sure any defective water draining systems, so any sump pumps and things like that. Any in any commercial buildings, you want to look for them as well. Heating, ventilating, and air conditioning units. Oh, you want to take a look at all those components, right? You want to take a look at the insulation on the refrigerant lines, make sure that's not damaged, especially in the attic, because that's going to cause condensation and emit that into the attic space. You want to make sure that all the ductwork is sealed, right? In human clients, one of the functions of the system is to reduce the ambient air moisture level or relative humidity throughout the building. So an improperly operating HVAC system isn't going to function and pull that humidity out. So you want to make sure that your units are functioning properly. Checking all flashings and sealant around all openings or transitions. Flashing, right, which is typically a very thin metal strip. You'll find that around doors, around windows, around head walls, chimneys, windows, roofs, is designed to prevent, right? Flashing is preventing water intrusion. So you want to make sure that the flashing is pitching away from the house, that it's properly installed, that it's secured, that it's not rusted or corroded. Right. And and you want to make sure it's sealed properly if there's any sealant on it. All right. Vents. All vents should have appropriate hoods, louvers, or screens on them. Okay. And they should all vent to the exterior of the home. So bathroom fans, laundry fans, any vents that you're using for any mechanical rooms, you want to vent them outside. And you want to make sure that they're not blocked or restricted with anything. Your HVAC system, you want to check for any leaks in the supply return lines, pumps, the air handlers, and other components. Drain lines should be cleaned and clear of instructions. Ductwork should be insulated. All right. So, and any unconditioned areas, you want to make sure your ductwork is wrapped with insulation. Okay. And that all that insulation is tight and strapped to the ductwork itself, even around the boots that go out of those units, so that there's no loss of heat inside those unconditioned areas. Humidity. All right. So, except in specialized commercial facilities, the relative humidity in your building should be between 30 and 50%. So, unless it's like a greenhouse, you don't want the humidity to be above that, or a hospital or something like that. But in your standard residential home, 30 to 50%. Condensation on any windows, wet stains on walls and ceilings, and musty smells are signs of excessive humidity. Okay. If you're concerned about the humidity levels in the building, consult with a mechanical engineer, contractor, or air conditioning repair company to determine whether your HVAC system is properly sized and in good working order. A mechanical engineer should be consulted when renovations to interior commercial spaces are planned. So a lot of times you'll see staining on in bathrooms or laundry areas. If you see it starting at the top and it's trickling down on the walls, that's an indication that the condensation and the humidity in those areas is excessive. And something isn't pulling that humidity out, whether it's a bath fan that's needed, or whether it's just too much moisture in that area. Damp areas, so damp or wet areas should be regularly cleaned and thoroughly dry. So you want to obviously keep any excess moisture sitting in your house and get it out. Expansion joints are materials between bricks, pipes, and other building materials that absorb movement. If expansion joints are not in good condition, water intrusion can occur. Interior finish materials, so any water damaged drywalls, plaster, carpet should be replaced. Water damaged ceiling tile should also be removed and replaced. All right. Exterior walls are generally compromised of a number of building materials. When properly designed and constructed, the assembly is the first line of defense between water and interior of your building. And it's essential that they be maintained properly, including regular refinishing and or resealing of the appropriate materials. Storage areas should be kept clean, allow air to circulate to prevent potential moisture accumulation. So if moisture does occur, right, what you want to do is you want to shut off any valves if it is a water issue. That can be easily turned off in the event of any plumbing leaks. If water intrusion does occur, damage can be minimized by addressing the problem quickly and thoroughly. Inspectors should help their clients identify all water shutoff valves. So I always note in my home inspection, right, where the shutoff valves are for the main shutoff, the sprinkler shutoff, and then if there's any spigot shutoffs too, right? Those are kind of your important ones. And then obviously you have all your fixtures. Every fixture should have a shutoff. So where's that located as well? Water intrusion, that's not so obvious. So obviously a plumbing leak, you see it, you can identify that. But when you're doing an inspection and you should note if there's any visible water damage. It's not possible to see what happens to an attic space during the winter if you're inspecting it during the summer. There are a lot of things that are beyond the scope of our typical home inspection, including determining how moisture is controlled in the house, especially at your wall assemblies. This right illustration here shows brown stains on the ceiling, and on the ceiling where the wall caused by moisture condensing on the cold roof sheeting in the attic. The water vapor has moved into the unfinished space through the open space around the leaking bathroom vents and leaking light fixtures. This illustration shows the potential complexity of moisture movement air movement, temperature condensation, and the resulting indications that may be observed during a visual only home inspection. So anytime you have leaky penetrations and you're heating your house, all that hot air is going into the attic. It's going to form condensation in there. Um, and you can see where they are depicting those water droplets on there. So it's important as home inspectors to show these areas to your clients, and then what can potentially be a fix there. Okay, um, so notating all of that. All right, so we're going into insulation now. As you can see, this is a depiction of all the different types of insulation. Heating and cooling account for 50 to 70% of the energy used in the average home inside the United States. Okay. Inadequate insulation and air leakage cause a lot of wasted energy in most homes. So insulation is great. It helps us save money, conserve our energy consumption and resources, makes your house feel comfortable, quiet, maintains uniform temperatures throughout the house, and makes a house obviously warm in the winter and makes a house feel cool in the summertime. How insulation works. Insulation provides resistance to heat flow. The more heat flow resistance the insulation provides, the lower the heating and cooling costs will be in your home. Heat flows naturally from a warmer space to a cooler space. In the cold winter, this heat flows moves directly from all heated living spaces to adjacent unheated spaces, such as attics, garage, basements, underfloor crawl spaces, and even to the outdoors. Heat flow can also move indirectly through interior ceilings, walls, and floors. Wherever there is a difference in temperature during the cooling season, heat flows from the exterior of the building. To keep the occupants of the building comfortable, the heat lost in the winter must be replaced by the heating system, and the heat gained in the summer must be removed by the cooling system. A properly insulated home will decrease the heat flows by providing an effective resistance to the flow of heat. Insulation in the form of bats, blankets, loose fill, and low density foams all work by limiting air movement. The still air inside the insulation is an effective insulator because it eliminates convection. Still air also has low conduction, so heat doesn't flow very well via conduction through insulation. Some foams are filled with special gases that provide additional resistance to heat flow. Reflective insulation limits heat that's transferred into the form of radiation. Some reflective insulation also reduces air movement, but not as much as other types of insulation. Don't confuse insulation's ability to limit air movement with air sealing. Insulation reduces air movement only within the space it occupies. It cannot limit air movement through other pathways nearby. For example, the insulation in a wall cavity doesn't affect the air leakage that may take place around a window frame. Adding insulation will likely not have the same effect as air sealing. Okay. Insulation's resistance to heat flow is measured or rated in the terms of thermal resistance, better known as its R value. The higher the R value, the greater the insulating effectiveness it'll be. The R value will depend on the type of insulation. Type of insulation, which includes its material, its thickness, and its density. The effectiveness of the insulation's material resistance to heat flow also depends on where the insulation is installed. For example, insulation that is compressed will not provide its full R value. The overall R value of wall or ceiling will be somewhat different from the R value of the insulation itself because heat flows more readily through studs, joists, and other building materials, known as thermal bridging. In addition, insulation that fills building cavities densely enough to reduce airflow can also reduce convective heat loss. The illustration shows how thick an insulation type must be in order to achieve that same R value. So here's your zones, right? For your R values. So your R values are all going to depend on where you're located throughout the country. All right. So this is kind of a neat like depiction that I put it in my reports as well with when I comment on, insulation is insufficient and what your insulation should be based on your location. Okay. So the amount of insulation or R value needed in the home is going to depend on its climate, type of heating and cooling systems, and the particular part of the house where the insulation is installed. The DOE has recommendations for new and existing homes in relation to its R value. The insulation recommendations for ceilings, wood frame walls, floors, foundation walls, crawl space walls, slabs have been increased overall and generally exceed those required by most building codes. The DOE's range of recommendations is based on comparing future energy savings to the current cost of installing insulation. You can use the map and tables in this section for new and existing homes as a reference guide for your inspection and evaluations of their insulation. If you observe insulation material used in layers, such as framing cavity, insulation, and insulating sheathing, the material can be summoned to compute the component's R value. Climate zones, are used to determine applicable requirements in home energy efficiency design and construction. The basement walls, exterior walls, floor, roof, and any other building elements that enclose conditioned spaces or provides a boundary between conditioned space and unconditioned space is called the thermal envelope. Okay, so if you follow the annotations in the bottom right-hand chart, R values are your minimums. All right. When insulation is installed in a cavity which is less than the label or design thickness of insulation, the installed R value of that insulation shall not be less than the R value specified in the table. So 15/19 means R15 continuous insulation on the interior or exterior of the home, or R19 cavity insulation is installed on the interior of the basement wall. 1519 shall be permitted to be met with R13 cavity insulation on the interior of the basement wall plus R5 continuous insulation on the interior exterior of the home. 1013 means R10 continuous insulation on the interior or exterior of the home or R13 cavity insulation at the interior of the basement wall. R5 shall be added to the required slab edge R values for heated slabs. Insulation depth shall be the depth of the footing or 2 feet, whichever is less than in zones 1 through 3 for heated slabs. Basement wall insulation is not required in warm, humid locations as defined by the figure 1101.1 and the table below. Or insulation sufficient to fill the framing cavity of R19 minimum. The first value is cavity insulation. Second is continuous insulation or insulated siding. So R13 plus 5 means R13 cavity insulation plus R5. And then the second R value applies when more than half the insulation is on the interior of the mass wall. All right, so we're going to go into where to insulate. All right. So this is another great thing to add to your guys' reports. Especially when you're calling out missing insulation in certain areas. Okay. Um, so insulation that is compressed, right, is not going to provide its full R value. The overall R value of a wall or ceiling will be somewhat different from the R value of the insulation itself because the heat flows around the insulation through the studs and the joists. If denser, heavier insulation is installed on top of lighter insulation in an attic floor area, the overall value may be different. If R19 batt insulation that's sized for 6.5 inches is stuffed inside a 5.5 inch wall cavity, that effectiveness is going to decrease. So it's important to install the proper size insulation inside the proper wall cavities. Not something as inspectors we're going to be able to see unless you're doing, you know, pre drywall inspections. If the insulation is installed in the wall cavity with electrical wires or plumbing pipes, the fiberglass bat insulation may be compressed there too. And that's going to decrease, obviously, the R value as well. It's important that insulation is obviously properly installed because that's how you're going to achieve the maximum R value. Insulation in between studs in a wall does not restrict the heat flow through those studs. This heat flow is called thermal bridging. The overall R value of that wall may be different from the R value of the insulation itself. It is recommended that the insulation installed in an attic covers the tops of the attic floor joists. It is also recommended that insulation sheathing be installed on wall studs. Wood studs can transfer energy through the wall assembly. Metal studs can transfer energy much better than wood studs can. As a result, metal walls offer overall R value can be as low as half the insulation R value. You may be asked by your client, does the home I'm about to buy need more insulation or does it have good insulation? I always get that question too. Unless the home was specifically constructed for energy efficiency, the homeowner can probably reduce the home's energy bills by adding more insulation, right? More insulation, always better. But air sealing is crucial. A lot of people will think that not sealing a bunch of protrusions versus just throwing more insulation over it. Again, insulation will reduce it. It's not going to prevent it. But air sealing is critical. The homeowner must air seal in order to actually reduce or stop that air movement. Check the attic walls, the floors, adjacent to any unheated spaces like a garage or basement. Structural elements are usually exposed in those areas, which makes it easy to see what type of insulation is installed and to measure its depth or thickness. Inspect and measure the thickness of any visible. If the crawl space isn't ventilated, it may have insulation in the perimeter wall. If the house is relatively new, it may have insulation outside the basement or foundation walls. Again, you're not going to see that. Adding insulation may require hiring a professional contractor. If the house is older, the electrical system should be checked by an electrician. If the wiring is degraded, overloaded, or the use of knob and tube wiring, it's hazardous to add insulation when conditions exist. Adding thermal insulation within a closed cavity around wires could cause the wires to overheat. Code does not allow the installation of loose fill, rolled, or foam in place installations around knob and tube wiring. All right. Adding insulation in a mobile home is complex and usually requires special expertise. Adding insulation over existing insulation should not include a vapor diffusion retarder between the two layers. So you don't want to have a faced insulation, right? The paper faced insulation doesn't matter which way it's installed correctly or up or down. You don't want to double vapor retarder it. All right. So check your attic, right? You always want to take a look at your attic spaces, right? Attic floors. Be careful where you step, right? Always want a safety first. Walk only on the joists so that you don't obviously fall to the ceiling below. If there is insulation installed and it's near the top of the joist, then it's a good practice to install bats perpendicular to the existing ones. That will help cover all of your joists and it's going to help reduce the bridging, the thermal bridging through those joists and into the attic. All right, the framing members. So when you go into your house, you're going to see different types of insulations, right? You'll see the loose fiber, fiberglass. It could be rock wool, cellulose. If you see granules, it could be vermiculite or perlite. And then obviously bats is the most common fiberglass bats. The attic access. All right, so attic access is it usually going to be a hatch. It could be a pull down set of stairs or a door if you're lucky. A non-insulated attic door will reduce energy savings substantially. I always will take my thermal gun before I even open the attic hatch, and I will scan it to see if it's insulated or not. And I always take a picture and put that in my report, or I'll take a picture of the backside of it showing that it's not a insulated door and how much you can see how much energy loss is being lost through. You can show the clients, which is pretty cool. Ideally, the attic access should be located in an unconditioned part of the house, if possible. Otherwise, the attic access should have weather stripping and insulation. The attic's access opening could be covered by an insulated cover box sometimes. You'll see those little either it's a like reflective material or sometimes people build them out of like rigid foam insulation. There should be an access opening to all attics that exceed 30 square feet and have a vertical height of at least 30 inches or more. The rough frame opening should be at least 22 by 30 inches, and it should be located in a hallway or other readily accessible location. An attic access that is located in a closed closet is often inaccessible due to shelving or clothes or people's personal belongings. For ceiling access openings, there should also be at least 30 inches of headroom in the attic space above, opening measured vertically from the underside of the roof framing members. All right. Because you're going to lose a lot of energy loss through those attic accesses. So it's important to take a look at them and make sure that they're sealed, guys. All right, so your pull down stairs. This right here, I don't know if you guys can read it, but it is an HVAC equipment. So that is the depiction of an HVAC air handler unit located in the into an attic space, if you can see. And over here too would be your opening. If there's a plumbing or electrical system or mechanical equipment in the attic space or under floor crawl spaces, then the space should be accessible for inspection, service, obviously removal or replacement. In addition to adequately sized access opening, a passageway should be provided in your attic made of solid flooring that leads from the opening to the equipment that needs to be serviced. There should be a space and clear unobstructed passageway large enough to allow removal of the mechanical appliance. Um, and the opening should be at least 22 by 30. The opening should be large enough for a person to get through it and for equipment to be removed. The passageway beyond the opening should be at least 30 inches high and at least 22 inches wide and not more than 20 feet in length from the opening. There are some exceptions. The passageway flooring should be at least 24 inches wide as well. A service area is required in front of the mechanical equipment, and we recommend a minimum of 30 by 30. A light fixture should be installed to illuminate the passageway and the mechanical appliance itself. And then there also should be a control switch near the entrance to obviously turn on the lights. And then an electrical receptacle should be installed as well in this area to provide for any convenient maintenance and servicing of the appliance. Attic pull down stairs, also called attic pull down stairs or ladders, and are collapsible ladders that are permanently attached, right? So that's what constitutes a pull down stairs. Occupants can use these ladders to access their attics without being required to carry a portable ladder. Common defects for these attic access stairs observed in consistently shoddy work that rarely meets today's standards, right? So a lot of times with these ladders, right, they cut the bottom cord of the structural truss. Often homeowners install them. Now, when you're not supposed to engineer, excuse me, you're not supposed to cut or alter a roof truss system, right, without having an engineer evaluate it and approve it. So a lot of times we see that from homeowners. A lot of times we see drywall screws, improper fasteners, nails, or they're installed in the incorrect areas. And that's going to reduce that they have a reduced shear strength drywall screws, and they're not there to support the extra weight of those of the framing of the attic stairs. Sometimes they're fashioned with insufficient nails. Manufacturers provide a certain number of nails that they and where they want them. A lack of insulation. Many times, hatches in many houses, especially older ones, they don't have any weather stripping. There's no insulation on them, and they're in conditioned spaces like in hallways. A lot of times we find the mechanisms on them, they're damaged, either the counterbalances are bent. Sometimes these stairs are cut incorrectly at the bottom, so they don't sit on the floor, and then they're not supported properly when you're going up them. They're loose, so they're cut short. Sometimes they're cut too long. A ton of times they put these in and they don't, and they're compromising um, the fire rating in garages and other spaces. So definitely before you guys go up in these attic stairs, make sure you take them down, check them, go up them, look at all the fasteners, make sure there's no damage to them before you go up them. And always pull those ladders down slowly because sometimes they have the ones that slide down and they come sliding down pretty quickly. All right, so attic rulers and thickness of the insulation. So you won't really see this with batt insulations, but the attic rulers you're mostly going to see with cellulose or blown in insulation. So a professional installer is going to attach a vertical ruler or an attic ruler to the joist of the attic prior to installing the blown in insulation. The installer should provide a signed and dated state describing the dated statement that describes the insulation installed, its thickness, the coverage areas, its R value, and the number of bags that they use. And this should be located in the attic. Insulation manufacturers provide similar charts on their product bags. The chart states the minimum number of bags that's needed to be installed per 1,000 square foot, and that's to obtain a specific R value for your area. If the attic has blown-in insulation, check the corners, right, and the hard to see areas, which is tough because a lot of times you can't enter these attics. But get a bright flashlight and try to extend yourself into those areas to see. It's common for those areas to not have insulation installed at this at the level that it's supposed to be. Insulation should be evenly distributed over the entire attic space. There also should be a little area around the scuttle hole that will can keep that insulation out of the scuttle area so it doesn't fall down into you or into the area when you open that up. Additionally, baffles, right, should be installed. So you should see them to prevent blocking the airflow through the attic vents, particularly at the eaves. Insulation should be blown all the way to the top plate of the exterior wall, because that's where you have gaps and you will get air leakage. Recessed lights should be properly filled in and covered. Insulated contact rated fixtures should be installed because they're airtight and can be covered with insulation. Again, it's going to be a hard thing for us to evaluate when it's covered with insulation, but you want to make sure if you're doing pre-drywalls and things like that, it's something that you mention. Check underneath any pieces of wood or platforms in the attic. Those areas need to be insulated as well. All right, so if there is a platformed area, you want to try to look on both sides of that to see if there's insulation around it. If there's mechanical equipment or storage areas that are located in the attic, the flooring system or platform decking should be elevated to allow the full height or thickness of the insulate to be installed. And also you guys want to check around all your plumbing, your ductwork, your wires to make sure all that insulation is sufficiently around it and keeping it tight and even around. All right, knee walls. So your attic knee walls, another thing you want to try to take a look at. Knee walls are vertical walls in attic spaces directly behind them. You'll typically find them in houses with either finished attic spaces and dormered windows, as with 1.5 story type homes. There are a couple ways that you may see a knee wall insulated. Okay. The most important areas and most overlooked areas to insulate are the open joist ends below the knee wall. All right. So you can kind of see in the picture here, the open joist ends below a knee wall should be plugged or stuffed with either squares of cardboard, metal flashing or rigid insulation, cellulose insulation blown in at a high density, or batt insulation stuffed into plastic bags. The plug should be sealed to the joist using either caulk, sealant, or spray foam. The knee wall and attic floor in the attic space behind the knee wall should be insulated. Sometimes string wire or cardboard is used to hold the insulation in place at the backside of that knee wall. Another way to insulate this area is to seal and insulate the rafter spaces along the sloping ceiling of the knee wall attic space. The rafters should have proper insulation and ventilation as required. One advantage of this approach is that after properly insulating, any ductwork that was in the small space is now inside a conditioned space. All right, so that helps put the ductwork or any plumbing inside the conditioned area of the house, so you don't have to insulate them separately. Check the exterior. Okay, so here's your standard exterior wall assembly, right? Breakdown. So an exterior wall of a building should be properly sealed, protected from moisture, and insulated adequately to increase comfort, reduce the noise, and save on energy costs. Exterior walls are one of the most complex systems in a building. A drainage plane in a wall system makes an easy pathway for water to drain away from the house. Rain leaks cause a lot of problems from walls. Water penetration into a wall can be the result of improper installation of the siding, poor flashing installation, bad weather stripping, poor caulking around joints at the building exterior, and wind-driven rain into and through the exterior siding material. A drainage plane in the wall assembly protects against water intrusion. All right, so we're not going to obviously peel back any siding to take a look at this wall, but usually you'll see indications inside, right, around windows or outside around the flashing. So those are definitely areas we want to look at. I always take special note of areas that are inside the house. And when I'm outside the house, I mean, starting my inspections to say like, okay, this wall has some really shoddy, whether it's heavily sealed caulking around flashing, or if it has no flashing at all, then I'll say, okay, that's second floor bedroom. I want to take a look at really closely when I'm inside. Um, an effective wall, right, has all the following characteristics. It's going to be airtight, so all air leaks should be sealed in a wall during construction and before the insulation is installed in it. It's going to control moisture, so it's going to get the moisture away from the house and prevent any moisture from entering the house. And then it's going to have complete insulation coverage as well. So the wall framing should provide enough room for complete maximum insulation coverage and reduce your thermal bridging with no gaps or compressed insulation. Benefits of air sealing, again, it's going to reduce your heat flow from air movement or convection. Air sealing prevents water vapor in the air from entering the wall assembly. Um, and air sealing is 10 to 100 times as important as installing a vapor diffusion retarder. Houses in all climates will require the following to control moisture. So you want a polyethylene sheet that should cover the exposed dirt in houses with crawl spaces. So a vapor retarder and the basement or vapor barrier. The grading around the house should always slope away from that foundation. Okay, you want a positive grading. A continuous vapor diffusion retarder with a rating of less than 1 should be installed. A termite shield, okay, on the top sill plate, below the sill plate and above the foundation top, or a sill gasket or other vapor impermeable membrane should be installed. All right. So you also want to check your floors. All right, so there should be an access hole through the perimeter wall of the crawl space. It should be at least 16 by 24 inches. If the access is through the floor, then the minimum dimension should be 18 by 24. Look at the underside of any floor that is located over an unheated space, such as a crawl space, basement, or garage. Check and measure the insulation that is installed there. It will likely be fiberglass batt insulation. The insulation may be identified with its R value printed on it. If it's not, multiply the fiberglass batt thickness by 3.2 to figure out the R value. If the insulation is foam board or spray foam application and you can't find any labeling, you can multiply its thickness by 5 to get a good estimate of its R value. If there is a floor over a crawl space, check for the presence of insulation installed underneath the floor. Also, check to see whether the crawl space is ventilated. You may discover that the floor is not insulated and the crawl space is not ventilated, but the perimeter walls are insulated. If there is a floor over a crawl space, check for the presence of insulation. All right. When bats or rolls or insulation are installed on the underside of a floor above an unheated crawl space or basement, insulation should be fitted between the beam and joists, pushed up against the floor overhead as securely and snugly as possible, installed without compressing it, held in a place with netting or snap-in wire holds, cut off and stuffed into tight spaces by hand, cut and fitted around cross bracing between floor joist and any other obstructions, installed against the perimeter band/rim joist that rest upon the sill plate, and installed on the ducts and pipes passing through the unheated space. Reflective systems are installed in a way similar to bat insulation. It's important to install reflective insulation properly for it to be as effective. Sometimes reflective insulation will have flanges stapled to the framing members. This conductive material must not come in contact with any electrical current. You may find spray foam insulation at a floor system. The spray can do an excellent job of insulating and filling in the spaces around electrical wires, pipes, and any other obstructions. In a non-ventilated crawl space, you may see fiberglass blanket insulation installed in the perimeter walls attached to furring strips. You may also see insulation fastened to the sill plate and draped down the perimeter wall to the crawl space. The insulation may continue over the crawl space floor for a couple of feet on top of the required vapor retarder or barrier. Foam insulation installed on the walls of a non-ventilated crawl space may be bonded to the wall using adhesive. If any insulation is exposed, consider checking the local fire codes and the flame spreading ratings of that insulation. If your client's home is in an area prone to termite infestations, be sure you communicate to your client about the inspection restrictions caused by the insulation. And, guys, with this spray foam installations, especially in the floor systems, we're finding in a lot of new constructions, it is limiting our ability to see a lot of things. So not just in your basement or crawl space areas, really should be calling it out even in your attics that it's limiting you, and making that note to your clients about that. It's kind of making our job a little easier, I think, but it's also making it a little more difficult, to really get and see how these systems are put together. All right, so ductwork. Um, so if you're going to enter the attic space, obviously be careful not to damage any cross ductwork. You don't want to compress it. It may be hidden. Then that's why you don't want to ever step on any insulation. You should only be stepping on either plywood or joists. Sometimes blown-in insulation will be layered over the ductwork in attic spaces, and it's going to be hard to see. So always proceed with caution. The ductwork of the HVAC system in a house may be checked by the inspector. If the ductworks run through unconditioned spaces in the house, such as crawl space or attics, then the ductwork should be insulated. The ductwork should not leak any air. Leaking joints should be repaired with mechanical fasteners and then sealed with water-soluble mastic and embedded fiber mesh. Gray cloth duct tape should never be used for this purpose. It degrades, cracks, and loosens its integrity and bond with age. If the joint is going to be opened in the future for maintenance or other reasons, then aluminum foil tape should be used. Um, I always make sure before I go in the attic, I crank up either the air conditioning or the heating system. That's whatever's passing through that. Because I want to be able to tell and see if I hear any leaks or can see any leaks within the insulation. So it's always important to run them. I also throw on all my bath fans or my kitchen exhaust or my dryer before I go in there Some people try to turn them off of me, but I always ask, can I please leave these on? 'Cause it's a good indication to see and make sure that these items are flowing out and through your attic and out. The ductwork should be wrapped with insulation that has a minimum R value of 6 with a vapor diffusion retarder facing on the outer exterior side. The insulation shouldn't be compressed, it should be overlapped and sealed with fiberglass tape where sections of the insulation meet. The insulation should not be torn or damaged. The vapor diffusion retarder should not be cut, torn, or damaged. The ductwork should not be compressed or damaged. These are all things that you want to obviously note. And if you do see duct tape, even if it's new, you definitely want to note that to your buyers that over time that duct tape will deteriorate and become damaged, even though it is sealing it now and there's no issues. Again, it's going to become a maintenance headache for them in the future. Uh, Types of insulation. All right, so you guys can see this is a type of insulation breakdown between your different insulations. The type of insulation is used, its R value, and the thickness needed are all directly related to the nature and the location of the spaces in the house. Right. Blankets come in the form of bats and rolls. They're flexible. They're made from mineral fibers, including fiberglass, rock wool, and they're usually available in different widths and lengths. They're made in standard sizes, widths for inserting in between studs and floor joists and ceiling. They're available with or without a vapor retarder faces or a paper face. Batten insulation, when installed in the ceiling of a basement with the insulation exposed, may have a flame-resistant face. Blown in, loose fill insulation may be made of cellulose, fiberglass, rock wool, or fiber pellets. The insulation can be blown in using a pump and hose system. This type of insulation can be blown into wall cavities. You may often see it blown into the attic floor. When the wall is being insulated, cellulose and fiberglass can be blown onto the wall. The insulation material is mixed with an adhesive or foam to make the insulation resistant to settling. Foam insulation can be installed by a professional using special equipment that meters, mixes, and sprays the foam insulation. There's obviously your open cell foams, and then there is your closed cell foams as well. And that's going to depend on your R value that and where it's being installed that you want to use that. Rigid insulation is made from fibrous materials and plastic foams. They are made into boards and molded pipe coverings. Rigid insulation boards may be faced with reflective foils that reduce heat flow when installed next to an airspace. You'll often find rigid insulation installed up against foundation walls, and it's used as insulated for wall sheathing as well. Reflective insulation is made up of an aluminum foil with a variety of different backings, including paper, plastic film, polyethylene bubbles, and cardboard. Reflective insulation is most effective in reducing downward heat flow. You'll often find them located between roof reactor boards, floor joists, and wall studs. If a single reflective surface is installed and it faces an open airspace, then it is called a radiant barrier. Radiant barriers are intended to reduce the summer heat gain and the winter heat loss. In new homes, you may see foil-faced wood components at the roof sheathing system installed with the foil facing down into the attic. There may be other areas where the radiant barrier is integrated into the building components and the structure of the home. For older homes, a radiant barrier will typically be found stapled across the bottom of some joists. All proper radiant barriers should have a low admittance of 0.1 or less and a high reflectance of 0.9 or more. The radiant barrier should not be laid on top of the attic floor insulation or on the attic floor anywhere, because it will soon be covered with dust and will not work. The U.S. Federal Trade Commission has clear rules about the R value label that must be placed on all residential insulation products. This label should have a clearly stated R value and information about health, safety, and fire issues as well. If you're inspecting a house during construction, you may request that the contractor provide the product label from each package. This will also tell you how many packages were used. We'll jump into roof insulation and ventilation. All right, so roof system, ventilation, and insulation are, again, a very important part for a number of reasons, including condensation control, temperature and heat control. energy efficiency of the home, and then preventative of any ice dam and formations. All right, so ventilation of attic areas is intended to prevent the accumulation of moisture vapor in the attic roof space and to dry low area levels of condensation that may form on the underside of the roof deck. Ventilation is also intended to reduce the temperature of the roof deck during hot periods to improve shingle durability. Reducing attic temperature through ventilation and insulation also improves energy efficiency during hot periods. And in the case of ice dams, elevated attic and roof temperatures during the winter can cause snow on the roof to melt. Insulation and roof ventilations help to keep the roof's exterior surface cold and minimize the development of melted water and consequently ice dams. Ventilating roofs in hot and humid conditions may add rather than remove moisture from attics and enclose roof spaces. However, not ventilating a roof may void the manufacturer's warranty and slightly decrease the life expectancy of the asphalt shingles due to the increased temperature of the roof surface. In colder climates, roof ventilation serves to remove humidity and condensation from the roof attic spaces and helps to prevent the chronic formation of the ice dams at the eaves. Tile, concrete, and metal roof materials are not similarly affected. It is possible to have an unvented attic space, but such a choice may require designing the roof structure space as a conditioned space, similar to that required when creating a habitable space in the attic. There are several sources that provide detailed information by designing an unvented attic. Traditional attic ventilation remains a cost-effective, um, imperfect solution for moisture control. Wood frame pitch roof systems are traditionally constructed with fibrous insulation materials installed on the ceiling plane or the attic floor along the sloped underside of the roof deck. Proper ventilation is critical for these types of systems. For vented wood frame pitched roofs, the primary concern is the potential for moisture to build up at the sloped underside of the roof deck during the cold weather. The underside of the roof deck is the condensing plane. Where vents are installed at the eaves, the insulation should not block the vents or the free flow of air. Where eave or cornice vents are installed, insulation must not block the free flow of air. There should be a minimum 1 inch space provided between the insulation and the roof deck sheathing. And at the location of the vent, the clearance can be provided by a rafter vent component, often referred as a baffle. The ridge vent itself may have external baffles and a weather filter, a mesh material, integrated into the vent's design to help prevent the entrance of any rain or snow through the openings of that ridge vent component. To completely cover an attic floor with insulation out to the eaves, the insulation or rafter vents, also called baffles, is needed. Complete coverage of the attic floor, along with sealing any air leaks, will ensure that the homeowner gets the best performance from the insulation. Rafter vents ensure that the soffit vents are clear and there is a channel for outside air to move into the attic at the soffits and out through the gable or ridge vent. To install the rafter vents, a contractor can staple them directly to the roof deck. Rafter vents come in 4-foot lengths and 14.5 inch and 22.5 inch widths for different rafter spacings. When the rafter vents or baffles are in place properly, the bats or blankets or blown-in insulation can be installed right out of the very edge of the attic floor. Blown-in insulation may be required, maybe an additional set of rafter vents or blocking material to prevent the insulation from being blown into the soffit. A piece of rigid foam board placed on the outer edge of the top plate works very well for this purpose. Lastly, code requires ventilation to be provided for each enclosed attic space and enclosed rafter space that formed where ceilings are installed at the bottom of the rafter boards. Each separate rafter space must be ventilated. The ventilation opening should be a minimum of 1/8 inch and a maximum of 1/4, protected with corrosive resistant wire mesh. Unvented roof systems and attic assemblies. All right. So when you have an unvetted roof system, usually you're going to see spray foam, whether it be open or closed cell, and fiberglass insulation can be performed successively at unvetted roof systems or unvented attic assemblies when air tightness is provided and humidity is controlled. There are many other important factors involved when inspecting unvented roof systems, including the climate zone, roofing solar and exposure properties, air vapor barriers, and interior humidity levels. For unvented roof systems, the condensing plane is the underside of the air impermeable foam. When they're properly installed, condensation should not exist because the temperature of the interior of the face of the foam should be about the same as the interior air temperature. To control air tightness, an air barrier system must be installed in the roof insulation assembly. An air permeable layer may be installed on the inside of the air permeable insulation, such as fiberglass or cellulose. To control both air and moisture movement for roofers sealed with spray foam insulation, air leakage is effectively stopped. Failure will be likely via accidental or unattended airflows at unvented wood frame pitched roof systems, such as around roof penetrations, including plumbing vents. So in new constructions, which we're obviously seeing a lot of this unvetted roof systems, you want to make sure that when the electricians come through or the guys doing the air conditioning unit or the plumbing, they just put their stuff in there and it's spray foamed around it. If they go and alter anything, then you're compromising that thermal envelope of the home and you're getting air leaks. That's when you're going to get issues, right? Uh, any unwanted attic assembly should meet the following conditions, right? Must be completely contained within the building envelope on any unvented space. Interior vapor retarders must not be installed on the ceiling, attic, or floor. At wood shingle or shake roofs, a vented airspace of 1/4 of an inch should separate the shingle shakes from the underlayment. An air impermeable insulation can be applied in direct contact with the underside of the roof deck for climate zones 5, 6, 7, and 8. Air impermeable insulation must have a vapor retarder in direct contact with the underside of the insulation, as long as air tightness is provided and humidity during the winter is controlled. Unvetted roof systems can perform successfully. You know, spray foam gets a lot of bad raps, and I don't think it's spray foam specifically. I think it is when someone doesn't understand how it's properly installed. Like there's a lot that goes in. Just spray foaming and then not doing anything like temperature controlling or humidity controlling in the house is going to make the issues, happen with spray foam. So when doing the spray foam inspections, you really want to look at everything else that goes into that building envelope. It's not just about the insulation itself. So inspecting roof ventilation in 10 quick steps here. All right. So inspecting a roof, right? You want to measure the area to be ventilated in square feet, right? Determine if there's a vapor barrier installed on a warm air winter side of the ceiling. Check the location of your vents. Check the type of vents. Remember to inform your clients that turbine vents and electronically powered vents need to be inspected, tested, and maintained annually. Determine if the enclosed attic space and the enclosed rafter spaces have cross ventilation for each separate space. Attics and enclosed rafter spaces must have cross ventilation. Measure the net free area of the vents. Determine whether the ventilation openings are protected against rain and snow. They should measure a minimum of 1/8 of an inch, maximum of 1/4 inch to be protected with corrosion resistant wire mesh. Calculate the required roof ventilation. If a vapor barrier is installed, multiply the area by 1 by 300. If no vapor barrier is installed and the vents are installed only in the lower portion of the space to be ventilated, below 3 feet of the vertical height of the space, then multiply that area by 150 or 50% to 80%. Of the vents are in the upper portion of the space to be ventilated and balanced of the ventilation is provided by the eave vents. Multiply that area by 300. Compare the calculations of the observed ventilation with the requirement for ventilation, where eave or soffit vents are installed. The insulation should not block the free flow of air. A minimum space of 1 inch should be provided between the insulation and the roof deck sheathing. Baffles are commonly used to provide that 1 inch of space. Ice dams. All right, so now we're getting into our winter months. This is when you're going to start seeing those ice dam forms. So it's it is tough to look at, but you can see when ice dams are starting to form. All right, and that's ice dams are caused by warming of attic space. All right, and while attic ventilation and insulation contribute to the prevention of ice dams by keeping attics cool, they can be overpowered by other attic warming effects, such as air leakage from the house into the attic through the ceiling, chases or open gaps, and then uninsulated ducts installed in the attic. If significant conditioned air escapes into the attic ventilation may not be capable of preventing the warming of the roof deck and the subsequent formation of ice dams. Therefore, sealing air leaks between the house and the vented attic is essential for making attic's ventilation work. Air leakage from the interior into the attic also introduces moisture. If a significant amount of interior air leaks into an attic, the ventilation in the attic may not be sufficient to prevent moisture and condensation problems there. For enhanced protection against the formation of ice dams, the table provides recommended insulation levels and vent area ratios as a function of the venting layout. These recommendations should be found in areas with a ground snow load greater than 30 pounds per square foot and in other areas where ice dams are concerned. The ventilation recommendations in the table can be used in addition to eave ice dam flashings to create multiple lines of defense. Also, the arrangement of vent areas must balance the high outlet and the low inlet vent opening. All right. When there's snow on the roofs, guys, too, I always look at my house in relation to other houses on the block. If you pull up to your house and there's snow on every other house on the block, but you're going to inspect the house and there's no snow on the house, chances are that that roof, right, has either poor insulation, has air leakage, is unventilated, right? So there's something going on there. So it kind of will stick out if you just kind of step back and look at all the roofs and say, okay, every one of the houses on the block that are facing the north all have snow on them, except the house I'm about to go into. So taking a look at that will kind of give you an indication before you even walk in what you should be looking for. So roof ventilation based on your climate. All right. A common problem with roof designs can be found at the eaves. There's often very little space for insulation of the required thickness to be installed at the eaves without blocking the soffit vents. Often the insulation is compressed in that area in order to fit the tight spaces, which then diminishes its R value. To correct that situation, some builders will install a truss roof with a raised heel or oversized cantilever. This type of truss has an elevated overhang that uses a combination of soffit and eave vents with baffles and soffit dams installed at the eaves. This type of truss provides plenty of room for insulation at the wall to roof intersection, as well as an additional window shading. All right. In stick-built roofs, some builders install an additional top plate across the top of the ceiling joist at the eave to raise the roof height. This additional top plate raises the roof height and prevents compression of the insulation and allows room for ventilation. Most building codes will require roof vents to expel moisture that could cause insulation or other building materials to deteriorate during the winter. In summer, ventilations may reduce the roof temperature and lengthen its service life. A combination of a continuous ridge vent along the peak of the roof and continuous soffit vents at the eaves provide the most effective ventilation. That's because your cold air is going to push that hot air up through your ridge vent, as you can see in the picture here on the left. All right, and that's going to allow for a continuous flow of air. It's not relying on any electric thermostatically controlled fans, any or anything like that. And it's continuous through the entire roof system rather than if there's just fixed roof deck vents in different areas. So cap vents and gable vents can supplement a roof design that has insufficient ridge vent area. Turbine vents can also be used. but they need an annual inspection and maintenance. Electronically powered roof fans are not ideal because they typically use more energy than they save. Now they have those the solar panel ones, which are pretty great. So those work pretty efficient too. Powered roof fans can also cause other problems. They're suck like when you have a powered roof vent, right? They're pulling air out of the attic, so they can pull also conditioned air from the house's interior through your leaking things like vents, protrusions, wall box like electrical boxes or lights, pulling airborne pollutants from the crawl space into the house's interior and causing exhaust gases from fireplaces and combustion appliances to enter the home, right? Researchers are still investigating whether attic ventilation is good for all climates. Until the research results are available and accepted, installation practices for attic ventilation should follow your local building code. All right. Every location is a little different on how we do things. But you definitely want to get familiar with the ventilation process, and be looking and providing that information to your clients. All right, so basement walls. So now we're downstairs. Finished basement walls are exposed to many different things that come from all directions. All right, the finished basement wall is exposed to different temperatures, different moisture levels, water vapor movement, heat, cold, cool concrete, warm interior air, and they all relate to the biggest concern with the basement finished walls, and that's moisture. All right, specifically exterior moisture. The approach for insulating and finishing basement spaces will vary, depending on whether you're dealing with new or existing construction and whether a basement is being only insulated but not finished. Exterior foundation insulation, so that uses foam insulation panels on the outside of the foundation wall, is commonly installed for new construction and is difficult to evaluate on existing homes. The exterior insulation foam panels on the outside of the foundation provide a moisture tolerant insulation layer on the outside of the foundation wall. This insulation layer moderates the temperature of the inside wall surface and can also be integrated with exterior water or damp proofing. If this type of insulation is installed, it requires shifting the house structure outward such that the sill plate overlaps the outer edge of the foundation insulation, protecting exterior insulation during construction and providing long-term protection from the exposed insulation, for the exposed insulation, excuse me. If there is foam insulation installed on the outside of the exterior foundation, look for building practices that overlap and protect the insulation. In new construction, above grade wood frame walls will typically be constructed of 2x6s that overhang the foundation wall. The overhang can be up to 2 inches. Additional rigid insulation can be installed that extends over the entire wall assembly. You may find foam insulation installed as the interior basement insulation. It offers good moisture performance, but it also requires being covered with a fire-resistant material such as drywall, gypsum. Foam is good for insulating a finished basement. A finished basement that is of high quality usually has some type of exterior waterproofing, relative humidity control in the basement, and air sealing. A dry basement is less likely to have problems with wood-destroying organisms. Once the exterior grading and groundwater factors have been addressed, the basement should remain dry and protected by properly installed wall assemblies. The basement finished walls need to be insulated to minimize cold surfaces. Cold surfaces, such as on the foundation wall, can create water condensation and raise the humidity level in the basement. The concrete foundation walls are below grade and are therefore relatively cool to the touch, especially if the finished walls are insulated. If the basement air tends to be warm and humid, particularly in the summertime, um, pass through the finished walls and comes into contact with the cool foundation walls, condensation may form and cause moisture problems, including damage and mold growth. The rim or the band joist area, which is the area that's directly above your foundation walls, is of particular concern because that area tends to stay relatively cool because that's exposed to the elements and you get that cool air that will sweep in through that area. A finished basement should be insulated around the perimeter of the basement exterior walls, and the basement ceiling should not be insulated. As a home inspector, you may see the problem where there may be insulation in between the finished basement space, the conditioned space, and the floor above. The finished basement wall should not be insulated with a type of insulation that is sensitive to water. It should be an insulation that is relatively water resistant. This technique, as well as traditional basement finish practices, is not intended to compensate for inadequate waterproofing, foundations drainage, indoor relative humidity control, or air leakage. If there are problems with water intrusion, drainage, humidity, or any air leakage, then the method of insulating the basement foundation wall will not matter. Insulating a basement on the interior side of the foundation wall is relatively new to residential construction as a best practice. Therefore, this strategy is included here primarily for your consideration. The insulation to use when finishing a basement is a rigid foam insulation board. That type of insulation will allow the foundation wall assembly to dry inward, away from the foundation wall and toward the interior of the finished basement space. The foam insulation should be vapor permeable, greater than 1 perm. The greater the perm, the easier it is for the wall to dry inward. Because the foam insulation needs to be continuous and sealed at all the seams, that insulation should be installed behind the wood framed wall. Additional insulation can be installed in the spaces between the studs. Humid air at the basement's interior should be prevented from leaking into the finished basement wall assembly and subsequently condensing. The interior side of the wall assembly should not have large holes in it. The ideal approach uses the gypsum wallboard as an air barrier and requires sealing any penetrations through and leaks around the panels. Air sealing of ceiling penetrations in the basement should also be addressed. Traditional practices, such as the use of warm air or warm in winter water vapor diffusion retarders on the inside of the finished wall systems, have resulted in moisture problems. Low permeability and continuous water vapor diffusion retarders, such as plastic sheathing and vinyl wallpaper on the inside of the basement finishes, should be avoided because that will trap the moisture vapor moving through the foundation wall. They also slow the drying process for newly formed foundations. Foam is a fire hazard. Okay, so semi-permeable rigid foam insulation and spray foam insulation on the inside of basement foundation walls is often found during an inspection of the full finished foundation of a house. Its use could be a good strategy for moisture-resistant finishing. However, fire and smoke characteristics of this type of insulation require that it be covered with a fire-resistant layer, such as drywall. Sometimes that requirement works fine when the basement is being finished. The requirement of having spray foam insulation be protected by a thermal barrier is found in the 2015 International Residential Code. In most cases where spray foam insulation is installed, the foam should be separated from the interior living spaces by an improved thermal barrier of at least a half-inch gypsum wallboard or 23 by 32-inch wood structural panel or a material tested to meet the acceptable criteria. There are a few exceptions to this requirement, including flame spread index ratings. If a basement will only be insulated and not finished, a fire-rated foam panel or similar fire-rated covering needs to be used because the above-grade portions of the basement wall can dry to the outside. Fire rating insulation on these surfaces may be an impermeable type. For example, it can have a foil facing, but insulating approaches that restrict the drying potential of below-grade portions of the foundation wall towards the inside should be avoided. So basement moisture. Gypsum wallboard, wood trim, and wood framing will wick moisture from the basement concrete slab. The concrete slab will tend to cool materials that are in contact with it, creating higher surface humidity levels that may support mold growth. Therefore, finishes and baseboard trim should be held up about a half-inch from the slab surface. This gap could be sealed with caulk or sealant to prevent air leakages from indoors. into the wall assembly. In addition, a thin foam plastic sill sealer may be used under the finished wall bottom plate for added moisture protection. During an inspection of a basement, check the bottom of the finished wall for moisture. So yeah, this is a great thing to do, guys. When you're going through your inspections, like looking at that base of the floor, and make sure the gypsum isn't wicking up that moisture. It's not touching the floor. Also, I always like to take a look if they have closets in basements. Always take a look at the back side of the closet doors. That's like a very big spot where we'll find fungal growth or mold growth on the back sides of those walls. And you'll look at the bottom of the molding and cabinets. A lot of times you'll see it there. If you're putting any materials such as gypsum or wood directly on that concrete slab, that moisture, that slab is damp and moist, and it is gonna pull up and wick that moisture up. All right. Insulation, moisture, and slab on grade. All right. So it's important to know something about insulation, moisture, and slab on grade, thickened edge and monolithic slab foundation construction. Appropriate moisture resistant site design and foundation installation should be checked during an inspection. In mixed and cold climates, careful attention should be given to the slab edge and the foundation's perimeter insulation to avoid thermal bridges, which can cause cold slab surfaces and condensation. The elevation of a slab on grade foundation should be a minimum of 8 inches above the exterior finish grade in areas with heavy rainfall. A clearance of greater than 8 inches or some other rain control measures may be installed, such as back vented cladding and an ice and water shield 18 inches up the wall. With a properly mound slab and functional site grading, surface water should drain away and minimize the moisture load around and beneath the slab. A vapor diffusion retarder of 6 mil plastic or other approved vapor diffusion retarder is generally required by standards below any slab intended as a floor for habitable spaces. The joint should be lap not less than 6 inches. It should be placed in direct contact with the underside of the concrete slab. The vapor diffusion retarder will prevent moisture vapor from adding to the building's interior moisture load and also serve as a break to the capillary movement of moisture. The capillary break layer, generally 4 inches of clean graded sand, gravel, crushed stone, or crushed blast furnace slag, further prevents bulk moisture from wicking up through the bottom of that slab. Cracks in your concrete floor. All right. So concrete will crack as a normal outcome of the curing process. Cracking can be worsened if uneven bearing conditions exist under the slab, such as an uncompacted fill area, excessive water. For the workability of the cement tends to produce excessive cracking, which can allow moisture to more readily penetrate the concrete slab, weakening the concrete and then leading to differential drying issues and cracking. Excessive cracking can allow additional moisture as well as radon gases to penetrate more easily through the slab. The use of welded wire fabric reinforcements provides a means of controlling the severity of cracking. The use of fiber reinforced concrete may also be provided for adequate crack control. Concrete control joints may be used to control random cracking by creating plain lines of weakness in the slab. Shrinking or curing cracks generally occur in any continuous length of concrete longer than 12 feet. As with basement foundations and footings, the local building code does not always require horizontal reinforcement of the thickened edge footing of a monolithic slab on grade. The same applies to a stem wall and independent slab construction. Some building practices may incorporate a minimum of a continuous number 5 rebar located horizontally at the top and bottom of the thickened edge of a monolithic slab or stem wall. This allows the thickened slab edge or the footing to act as a moderately reinforced grade beam to reduce cracking from differential settlement. Concrete and masonry stem walls may be reinforced with horizontal reinforcement bars in a manner similar to that recommended for basement walls. For difficult site soil conditions, other types of concrete slab foundations may be more appropriate, such as a mat foundation and post-tension slabs. All right, so insulating your slabs. Building codes allow foundation insulation to be placed at various locations at the perimeter slab. All right, the best locations for insulating a slab on grade is on the vertical outside face of the foundation. In this location, thermal bridges are minimized, energy efficiency is maximized, and slab surface temperatures are moderate to prevent the risk of condensation during cold weather. If slab on grade insulation is placed in a different location, then there should be a continuous thermal break between the indoor portions of the slab and the exterior. When used, exterior foundation insulation must be protected from the elements at an additional expense. One way a builder could reduce costs while installing exterior slab perimeter insulation is to use a frost-protected shallow foundation. These foundations are found in more northern regions. They're most cost-effective in climates where required frost depths are subsequently substantially greater than 12 inches, and foundation insulation requirements are more stringent. Frost-protected shallow foundations systems offer design options that allow for shallower footings by raising the frost depth around the building. Ideally, heated slab systems may be used with insulation amounts increased above that minimal required. All right. So just like basement wall finishes, finishes on concrete floors or slab on grades are exposed to a unique environment due to direct ground contact. From a moisture perspective, tile, stained decorative concrete, and other moisture-resistant finishes are ideal for slab-on-grade construction. These materials are resistant to flooding and other sources of moisture damage and are typically in southern hot, humid climates. In such cases, the primary concerns are limiting indoor humidity, providing a sub-slab vapor diffusion retarder directly below the concrete slab, and providing a capillary break. Carpet and wood-based floor finishes should not be applied directly to slab on grades unless the slab or finished surface temperature is raised near room temperature. Moderate floor temperatures that can accommodate moisture-sensitive finishes can be achieved with sub-slab or slab surface insulation, as well as perimeter insulation to prevent thermal short circuits into the slab. Where slab temperatures are chilled by cold exterior winter conditions or cooled by ground temperatures during the spring and summer, surface condensation or high humidity may result in mold or condensation damage. If a slab shows signs of pre-existing moisture problems, such as dampness or condensation, any salt deposits, or standing water, that issue should be addressed before moving ahead with finishing your flooring. Once any pre-existing moisture issues with the slab are addressed, a floor finish assembly can accommodate a small amount of upward moisture flow and can be one viable option involves the use of a rigid semi-permeable insulating sheathing, such as extruded polystyrene on top of the slab, with 12 to 16 inches on center furring above the foam, followed by a layer of T&G plywood for the subfloor. The finished flooring above the plywood should be a breathable finish, and permeable materials such as vinyl flooring should be avoided. The primary causes of moisture problems in crawl spaces include poor site drainage, lack of ground vapor diffusion retarders, improperly installed insulation, and crawl space ventilations during summer conditions. Crawl space moisture damage and mold formation can be caused by any of these issues. Therefore, these issues should be checked during your inspection. Crawl space construction should ideally result in an interior crawl space floor ground surface that is at or above the exterior finish grade. This is not often the case. Extra attention should be paid to foundation drainage for crawl spaces below the exterior finish grade. Also, venting crawl spaces in humid conditions can result in condensation of warm, moist air on cool surfaces in the crawl space, including ductwork and the underside of the floor framing system. In very humid conditions, this can lead to water accumulation, wet insulation, material degrading, and mold. Crawl space floors may be a mud slab. Ground cover material, such as a thick layer of plastic laid on a crawl space floor, can become damaged or disturbed over time, resulting in a loss of effectiveness. In addition, it's difficult to drain a crawl space's ground cover that may become occasionally wet on top, such as from a plumbing leak. To correct that condition, a mud slab, such as 2-inch thick concrete slab, may be placed on top of the ground cover and slightly sloped to drain to a sump pit. The concrete floor that you see inside a crawl space may be a mud slab. All exposed ground areas in crawl spaces should be covered with a minimum of 6 mil layer plastic sheathing. The edges of the sheathing should be overlapped at least 6 inches. The plastic should then be sealed with tape or adhesive at all overlaps and to walls and to all penetrations in the sheathing. This is a simple measure that helps control ground moisture effectively. If the ground cover initially installed is damaged during the construction process, an additional layer should be added or damaged sections should be patched and sealed. If the crawl space elevation is below the exterior finish grade, foundation drainage and foundation wall damp proofing using a bituminous coating on the below grade exterior face of the crawl space foundation wall should be installed in a fashion similar to that required for basements. There are essentially two choices for ventilation of crawl spaces. The first is conventional ventilated practices, and the second follows a non-ventilated crawl space design strategy. Vented, the underfloor crawl space between the bottom of the floor joist and the earth under any building except for a basement should have ventilation openings that allow air to pass through the exterior foundation wall. The ventilation opening should be at least 1 square foot for every 150 square foot. When a vapor retarder is installed and covers the ground surface, the minimum net area of the opening should be at least 1 square foot for each 1,500 square foot of underfloor area. The ventilation openings, previously mentioned, can be reduced where the earth ground surface is covered by a vapor retarder and ventilation openings are installed. As a best practice, exposed dirt on the crawl space floor should always be covered by a vapor retarder. Joints of the vapor retarder obviously should be overlapped and taped and secured. The inspector should refer to the local building codes before making evaluations regarding any defective installations. The second option is a non-vented crawl space. A second option, right? There is a mounting evidence as well as a recent recognition of model building codes that the non-vented crawl spaces are an acceptable method of crawl space foundation construction. So this method should be considered an option in other climates. However, there's more to it than simply taking out the vents, right? It's best in hot climates, but it can be done in other climates. When inspecting an unvented crawl space, the inspector should check the following factors. Exterior site drainage, right? That's always first thing to check. Air leakage between the exterior and the crawl space area. Make sure that everything is properly sealed. The use of a ground cover in the crawl space and that is covered 6 inches lapped and taped and sealed. Damp proofing of the foundation walls and the insulation exterior drainage system. And that's if the ground elevation is lower than the exterior finish grade. And then some ventilation of the crawl space with conditioned air. One of the following should also be provided, right? There needs to be a mechanical exhaust ventilation operating continuously, or a conditioned air duct in there. All right. Recent model building codes also recommend that non-vented crawl spaces be treated as conditioned basement spaces. That is, it's supplied with conditioned air along with a return grill placed on the floor above the crawl space. Alternatively, the crawl space could be mechanically ventilated or designed as an underfloor space plenum for the distribution of conditioned air. While non-vented crawl spaces designs without these features have performed well, inspectors should check the local building codes. The principal perceived advantage of a vented crawl space over a non-vented One is that venting can minimize radon and moisture-related decay hazards by diluting the crawlspace air. Venting can complement other moisture and radon control measures, such as ground cover and proper drainage. However, although increased airflow in the crawl space may offer some dilution potential for ground source moisture and radon, it will not necessarily solve an established problem. The principal disadvantages of a vented crawl space: pipes and ducts must be insulated against heat loss and freezing. A larger areas usually must be insulated, which may increase the cost. And in some climates, warm, humid air circulated into the cool crawl spaces can actually cause excessive moisture levels in the wood. Vented crawl spaces are often provided with operable vents that can be closed to reduce winter heat loss, but may potentially increase radon infiltration. Although not their original purpose, the vents can also be closed in summer to keep out moisture, exterior air, having a dew point above the crawl space temperature. It's not necessary to vent a crawl space for moisture control if it is open to an adjacent basement and venting is clearly incompatible with crawl spaces used as heat distributions plenum. In fact, there are several advantages to designing crawl spaces as semi-heated zones. Duct and pipe insulation can be reduced, and the foundation is insulated in the crawl space's perimeter instead of at its ceiling. This usually requires less insulation, simplifies installation difficulties, and can be detailed to minimize condensation hazards. Air leakage and moisture problems. Air leakage through building assemblies can move large quantities of water and is a major factor in many vapor-related moisture problems. Building envelopes should be constructed to reduce air leakages from inside to outside in cold climates. In addition, a suitable air barrier system should be carefully considered and installed during the construction process. Any one of the combinations of the following drives air leakage: wind, stack effect, forced air HVAC equipment, such as a central air handler. Wind and stack effect driven air leakage is best handled by the use of air barriers. HVAC equipment should be properly installed, and seams and connections in the distribution system should be airtight. There are a few precautions worth mentioning when the building envelope is tightened. First, the use of air barriers and air leakage sealing practices can reduce the supply of combustion air for fuel-fired equipment on oil or gas furnaces, gas water heaters, and gas dryers. Located within the conditioned space, this can result in negative pressure and backdrafting of the combustion products. The operation of spot exhaust fans, kitchen or bath, whole house exhaust ventilation, and even the stack effect can also cause depressurization of the indoor space near combustion equipment and lead to backdrafting and the introduction of combustion products into the home, such as carbon monoxide. Because of this health and safety concern, sealed combustion equipment is often installed when the house is tight or sealed. Second, mechanical ventilation may be required or recommended to address other consequences of tightening the building envelope, such as in indoor air quality and humidity control. For example, modern residential building codes still permit the use of operable windows as a means of providing fresh air ventilation. Through this has been contested in recent years. It may be risky to rely solely on the behavior of the occupant to provide adequate ventilation in the absence of higher levels of natural ventilation. As a final precaution, air barrier materials must be considered in terms of their impact on vapor movement and water shedding. For instances, if an air barrier is used on the exterior of the wall as a weather barrier underneath cladding or house wrap, it must have adequate water resistant qualities. And if the air barrier is used to the inside of the wall in the hot, humid climates, it needs to be permeable material and not one that will prevent vapor from drying to the inside. Air sealing is important because air carries both moisture and energy, usually in the direction that the homeowner does not want. Air leaks can carry hot, humid outdoor air into the house in the summer months. Air leaks can carry warm, moist air from a bathroom into a cool attic in the winter. Air can leak into the house from unconditioned spaces such as the attic, basement, and crawl space. So Where your clients might not be fully aware of are the other pathways for air leakages, including any cracks where two walls meet, any openings and cracks where the walls meet the ceiling, any opening and cracks near interior door frames, gaps around electrical receptacle outlets, switches, recessed light fixtures, gaps between recessed cabinets, false ceilings and soffits in the kitchen, behind bathtubs and shower stall units, through floor cavities or finished attic adjacent to unconditioned attic spaces, utility chaseways for ducts, pipes, and wires, and plumbing and electrical penetrations. Air sealing is an essential first step. It's important to stop the air leakage prior to adding insulation in these areas. Looking for big air leaks. To ensure that an air barrier functioned as intended, leaks in the building envelope and air barrier system must be reasonably controlled. The methods are generally low tech and common sense oriented. All joints and seams and penetrations, including utility penetrations, right, are sealed. Site-built windows, doors, and skylights. Openings between windows and door assemblies and their respective jambs and framing. Any knee walls. Drop ceilings, chases adjacent to the thermal envelope, wall cavities, chases that extend into unconditioned spaces, walls and ceilings separated in an attached garage from conditioned spaces, openings behind tub and shower enclosures on exterior walls, common walls between dwelling units and other sources of air leakage. Cathedral ceilings and air leaks. Cathedral roofs can hide leaks and condensation, particularly vapor diffusion retarders such as polyethylene sheathing is used on the ceiling side. Something that should be considered only for very cold climates. If there are cathedral ceilings in the house, the ceilings and any penetrations through it should be carefully sealed to prevent air leakage. This may involve special air sealed light fixtures, the use of caulks, and sealants at all penetration and joints, and avoid leaky sealing systems such as exposed tongue and groove boards. Leaking of humid indoor air into cold cathedral roof cavities is a major cause of condensation and moisture problems in this type of roof. For cathedral ceilings, there needs to be enough space between the roof deck and the ceiling for adequate insulation and ventilation. Adequate insulation thickness can be achieved when the builder uses either raised trusses, truss joists, scissor truss framing, and or significantly larger rafters. Remember that cathedral ceilings with 2 by 12 rafter boards have a maximum amount of space for a standard 10-inch R30 batt insulation. You may see foil face batt insulation used in cathedral ceilings because it has a 0.5 permeable rating and provides the permeable often required for the use in ceilings without attic spaces. You should see a vent baffle installed between the insulation and the roof decking to ensure proper ventilation. If the roof framing at the cathedral ceiling cannot provide enough room for proper ventilation and insulation, then you may see furring strips attached to the underside of the rafter boards. The furring will provide enough room for thicker insulation to be installed. Some builders will install high density batts in tight areas or add rigid foam insulation under the rafters. Rigid foam insulation is a good choice because of its ability to resist thermal bridging through the rafters. So vapor diffusion retarders, all right. The amount of vapor diffusion that occurs in a building is determined by two things: the driving force that pushes it, known as vapor pressure, and the permeability of the material that's being used. Most materials, even glass, are unable to completely stop vapor diffusion. Thus, calling something a vapor barrier is a bit of a misnomer. The current trend in building sciences is referred to materials as vapor retarders, meaning that while they retard or slow down the movement of water vapor, they do not completely halt the process. Typical building codes are consider a material to be a vapor retarder if it has a permeable rating of 1 or less. Vapor retarders are often installed in the crawl space of a building to prevent ground moisture from evaporating and traveling up into the home. Many building codes require applying such vapor retarding materials under wall boards to prevent vapor diffusion from bringing water into the structural assembly in cold climates during the heating season. Pressure differential drives the vapor from the inside of the building to the outside. For example, in Minnesota, The vapor barrier is generally installed on the interior face of the wall studs. In warm climates during the cooling season, this vapor drives it from the outside of the building towards the inside. Thus, in Florida, vapor retarders are often applied to the outside of the buildings beside the permeable rating of the material, and the effect is vapor retarder is also a function of its surface area. For example, a vapor diffusion retarder that covers 80% of buildings is said to be 80% effective. It is a myth that installing a vapor retarder is the most important step for controlling moisture in walls. Vapor retarders only retard moisture due to diffusion, while most moisture enters walls either via fluid capillary action or as a vapor through air. All right, so in 2015, the IRC defines vapor retarders based on their permeability, the ability of a material to retard the diffusion of water vapor is measured in units known as perms or permeability. The higher the perm rating, the more easily water vapor can pass through the material, right? So your class one vapor retarders include glass, sheet metal, unperforated aluminum foil, polyethylene sheets, and rubber membranes. In older homes, class one vapor retarders were often installed on the interior side of the walls in all climate zones. If the walls are very drafty due to the lack of insulation and air sealing, drying can occur. When insulation and air sealing are added, consideration should be given to any existing vapor retarders or minimize the likelihood of condensation problems. Class 2 is anything unfaced or expanded extruded polystyrene, 30-pound asphalt coated paper, and plywood bitumen coated craft paper. Class 3, gypsum board, fiberglass insulation, unfaced, cellulose insulation, board lumber, concrete block, brick, 15-pound asphalt coated paper, house wrap, and latex or enamel paint. So ventilation of interior house air. So unless properly ventilated, an airtight home can seal in indoor air pollutants. Ventilation also helps prevent moisture. Another important consideration for a healthy, energy efficient home, historically homes did not have requirements for ventilation because air leaks through the building envelope and natural ventilation were considered adequate. As envelope construction techniques and materials have improved, the need to control indoor air quality in the home has increased. Today, many residential building codes require a home to have adequate mechanical ventilation systems installed with controls for the occupants to use. Each mechanical system should have a supply, an exhaust, or both, and have a relatively accessible switch or other means to shut the unit off. Automatic or gravity dampers that close when the system is not operating should be installed at the exterior of the home. Some terms to know: mechanical ventilation, natural ventilation, and then CFM, which is cubic feet per minute. All homes need ventilation. The exchange of indoor with outdoor air to reduce moisture, indoor pollutants, and odors. Contaminants such as formaldehyde, VOCs, radon can accumulate in poorly ventilated homes and cause health problems. Excess moisture in a home can generate high humidity. High humidity can lead to mold growth and structural damage to the home. To ensure adequate ventilation, and says the ASHRAE says that a home's living area should be ventilated at a rate of 0.35 air changes per hour or 15 cubic feet per person per minute, whichever is greater. A home can be ventilated in the following three ways: through natural ventilation, which is an uncontrolled air movement into home through cracks, small holes, vents, such through windows and doors. A whole house ventilation is controlled air movement using one or more fans or a duct system. And then spot ventilation is controlled by air movement using localized exhaust fans to quickly remove pollutants and moisture at their source. Natural ventilation used to be the most common ventilation for allowing fresh outdoor air to replace indoor air. Today, it's usually not the best ventilation strategy, especially for homes that are properly air sealed um, or for energy efficiency. Natural ventilation occurs when there is uncontrolled air movement or infiltration through cracks and small holes. Because of the central heating and cooling systems, however, most people don't open windows and doors as often for natural ventilation. Therefore, air infiltration has become the principal mode of natural ventilation in homes. A home's natural ventilation rate is unpredictable and it's also uncontrollable. It can be relied upon to ventilate a house interior uniformly. Natural ventilation depends on a home's air tightness, outdoor air temperature, wind, and other factors. Therefore, during mild weather, some homes may lack sufficient natural ventilation for the removal of indoor air pollutants. Tightly sealed and or tightly built homes may have insufficient natural ventilation most of the time, while homes with high air filtration rates may experience higher energy costs. Whole house ventilation provide controlled uniform ventilation throughout a house. These systems are usually one or more fans and duct systems to exhaust stale air and or supply fresh air into the house. There are four types of whole house ventilation. So there's exhaust ventilation systems that force air inside air out of the home. Supply ventilations that pumps air into the home. Balance ventilations, which force equal quantities of air inside and out. And then there's also an ERV system, which is an energy recovery system. And that transfers heat from incoming or outgoing air to minimize any energy loss. This type of ventilation system is covered in the next slide, which we'll go over that. Exhaust ventilation systems work by depressurizing the building by reducing the air pressure indoor to levels below the air pressure outdoor. This type of system extracts indoor air from a house while makeup air infiltrates through leaks in the building's shell. Exhaust ventilation systems are most effective in colder climates. In climates with warm, humid summers, depressurization can draw moist air into the building wall cavities where it may condense and cause moisture damage. An exhaust ventilation system is relatively simple and inexpensive to install. Typically, it's composed of a single fan connected to a centrally located single exhaust point in the house. An ideal design option is to connect the fan to ducts from several rooms, preferably rooms where pollutants tend to be generated, such as bathrooms. Adjustable passive vents through windows and or walls can be installed in other rooms to introduce fresh air, rather than relying on any leaks. One concern with exhaust ventilation systems is that they draw many pollutants along with fresh air into the house, such as mold spores from outside, radon, dust from attics, vapors, any flue gases, things like that. Supplying ventilation systems work by pressurizing the building. They use a fan to force air into the building while air leaks out of the building through holes in the shell. As with exhaust ventilation systems, supply ventilation systems are relatively simple and inexpensive. Supply ventilation systems allow better control of the air that enters the house than do exhaust ventilation systems. Pressurizing the house may prevent backdrafting of combustion gases from fireplaces and appliances. Supply ventilation also allows outdoor air that's introduced into the house to be filtered to remove pollen and dust, or it may be dehumidified to provide humidity control. Supply ventilation systems work best in hot and mixed climates because they pressurize the house. Supply ventilation systems have the potential to cause moisture problems in cold climates. In winter, the supply ventilation system causes warm interior air to leak through random openings in the exterior wall and ceiling. If the interior air is humid enough, some moisture may condense in the attic or the cold outer parts of the exterior wall where it can promote mold and mildew decay. Like all exhaust ventilation systems, supply ventilation systems do not temper or remove moisture from the makeup air before it enters the house. Thus, they may contribute to higher heating and cooling costs compared with energy recovery ventilation systems. Balanced ventilation systems, if properly designed and installed, neither pressurize nor depressurize the house. Rather, they introduce fresh air outside the air and exhaust polluted inside air in roughly equal quantities. A balanced ventilation system usually has two fans and two duct systems, and it will facilitate effective distribution of fresh air by placing supply and exhaust vents in appropriate places. Fresh air supply and exhaust vents can be installed in every room, but a typical balanced ventilation system is designed to supply fresh air to bedrooms and living rooms, where people spend most of the time. It also exhausts air from rooms where moisture and pollutants are most often generated, such as the kitchens and bathrooms, and perhaps a laundry room. Some designs may use a single point exhaust because they directly supply outside air. Balanced systems allow the use of filters to remove dust and pollen. Balanced ventilation systems are appropriate for all climates. However, because they require two ducts and fan systems, balanced ventilation systems are usually more expensive and operate than supply or exhaust. Energy and heat recovery ventilation systems provide a controlled way of ventilating a home while minimizing energy loss. They reduce the cost of heating ventilated air in the winter by transferring heat from the warm air inside being exhausted to the fresh but cold supply air. In the summer, the inside air cools the warmer supply air to reduce ventilation cooling costs. There are two types of energy recovery systems. There's a heat recovery and an energy recovery. Both types include a heat exchanger, one or more fans to push the air. There are some small wall and window mounted models, but most are central whole house ventilation systems with their own duct system or shared duct work. The main difference between the heat and the energy is the way the heat exchanger works. With an energy recovery ventilator, the heat exchanger transfers a certain amount of water vapor along with heat energy, while a heat recovery ventilator just transfers the heat. Because an energy recovery ventilator transfers some of the moisture from the exhaust air to the usually less humid incoming winter air, the humidity of the house's interior air stays more constant. This will also keep the heat exchanger core warmer, which will minimize problems with freezing. In the summer, an energy recovery ventilator may help to control humidity in the house by transferring some of the water vapor in the incoming air to the drier air that's leaving the house. However, there's some controversies about using ventilation systems at all during the humid months. Some experts suggest that the system off in the very humid air weather to keep indoor humidity low. A system can also be set up that runs only when the air conditioning system is running. Most energy recovery ventilation systems can recover about 70 to 80% of the energy in the exiting air and deliver that energy to the incoming air. However, they are most effective in climates with extreme winters and or summers, and where fuel costs are high in mild climates. Um, Energy recovery systems, they cost more to install than other ventilation systems. In general, simplicity is key to a cost-effective installation. To save on installation costs, many systems share existing ductwork. Complex systems are not only more expensive to install, but they are generally more maintenance intensive, often consume more electrical power. For most houses, attempting to recover all of the energy in the exhaust air will probably not be worth the additional cost. Energy recovery systems operating in cold climates must have devices to help prevent freezing, and energy recovery systems require more maintenance than other ventilation systems. They need to be cleaned regularly to prevent deterioration of the ventilation rates and heat recovery, and to prevent mold and bacteria from heat exchanger surfaces. Generally, these are located within your attic systems, and there is a filter inside those units. A lot of the newer construction homes that we're seeing, we're opening them up. Clients don't even know they have a filter in there. So make sure you're telling your clients, guys, that these need to be serviced annually. The filters need to be cleaned and checked so they're properly working. Spot ventilation improves the effectiveness of natural and whole house ventilation strategies by removing indoor air pollutants and or moisture at their source. Kitchens, bathrooms, lavatories, laundry rooms, utility rooms, and toilet rooms all have specific functions in the home. These functions produce pollutants such as moisture, odors, VOCs, particulates, and combustion products. The purpose of the spot ventilation is to control the concentration of these. Spot ventilation includes the use of localized exhaust fans, such as those used above kitchen ranges and in bathrooms. All right, and you want to pull that air respectively out of those areas, and they're designed to exhaust the odors and moist air to the home's exterior. The fan may be controlled in many ways. They have sometimes a timer switch. They can be controlled by just a normal switch or a wall-mounted humidistat that can be preset. Newer fans may be very quiet but work just fine. Older fans very noisy and loud. If an older fan is quiet, it may not be working as well. Inspectors can test for adequate airflow with a chemical smoke pencil. I always grab a piece of toilet paper and stick it up there and see. Just the easiest way, and it's cheap. Bathroom ventilation fans should be inspected for dust buildup that can impede airflow. Particulates of moisture-laden animal dander and lint are attracted to the fan because of its static charge. Inspectors should comment on dirty fan covers and bathrooms with only windows without a fan, since windows will not be open during the winter months in cold climates. The following conditions indicate insufficient bathroom ventilation: moisture stains on the wall, corrosion of the metal, visible mold on walls or ceilings, peeling paint or wallpaper, frost on windows, and high humidity. The most common defect related to bathroom ventilation systems is improper termination of the duct fans. The most common improper locations: attic, underneath insulation, inside the wall cavity, in crawl spaces or into unfinished areas. So always checking to make sure that they're terminating to the exterior of the home. Improperly terminated ventilation systems may appear to work fine from the inside, but their issue isn't the inside, it's the outside because you're putting all of that additional moist air to somewhere where you usually don't want that moist air. So if you're venting your bathroom or your kitchen into your attic, you don't want that moist air in there. It's going to condense and cause mold and other problems inside those areas. All right. And in your ductwork, it should be made of some flexible type material. It should contain a louver or screen that's vented outside. It may be insulated in some colder climates. And or if it vents on the roof, you want it to have a proper cap or screen. All right, so windows. Fixed windows are sometimes referred to as picture windows. Okay, so we see a ton of them. Double hung windows, obviously, that is a window that operates both sashes, so one goes up, one goes down. Many older homes have double hung windows. There's sliding windows, single hung windows. That's when one sash is going to be fixed, usually the top sash, and the bottom sash will slide up and down. They are casement windows that are on a hinge and that you crank out. Awning windows, it's essentially a casement window, but it just cracks where it opens on the bottom, not to the side. Then there's a hopper window, and then that will open from the top half. All right, similar to a casement window. In older houses, you may find jalousie windows, which consist of slots of parallel glass. Um, these are louvers are locked together onto a track so that they may be tilted open. When the window is closed, the louvers overlap each other in a single pattern. Jalousie windows are best suited for porches that are non-climate controlled. They're common on mid-century homes, in like southern states. They're also common in Hawaii. They're good for providing ventilation, but you don't want to use them they're not very good for energy efficiency. So if you see them, you should be calling them out. Transom windows, that's just a window that's located above a window. All right. Usually you'll see them in doors. And then there's also bay windows, which is multi-panel windows, and they're on different angles. All right. So window components, all right. So light refers to a glass pane. Several lights may be installed in a window. For example, a fixed window has one light. A single light can refer to one piece of glass or in a sash. A horizontal slider has two lights with one fixed sash, and the other a slider. A double light refers to two lights of a window. The muntins, the lights in a window sash, are divided horizontally and vertically by narrow strips of wood, or called muntins. Muntins divide a sash into smaller lights or panes. In many modern windows, these are not true. They're usually decorative or fake or plastic. Those are more for old school, like single pane glass windows that you see. A mullion is a structural element that divides adjacent window units. A mullion is often confused with a muntin or a glazing bar in the UK, which is the term for the small strip of wood or metal that divides a sash into a smaller glass panel or pane. Um, these act as mullions act as structural members, and it also carry the dead load of the opening. And then, we're in the Northeast, but I know in Florida, you guys, these may be engineered for wind load. So that's something for you guys that are in Florida that you definitely want to um, take a look at when you're looking at windows. Condensation in double pane windows. So condensation, obviously the accumulation of liquid on a relatively cold surface. Almost all air contains water vapor, which is in its gas phase of water and is comprised of tiny water droplets. The molecules in warm air are far apart from one another and will allow the containment of a relatively large quantity of water vapor. As it cools, they get closer together and they squeeze, the water vapors will form, and that's where you will get condensation. Household air is humidified from air from high levels of water vapor in human and animal exhalation, plant transportation, and household appliance and fixtures such as showers and dryers. The humidity can rise significantly higher than the exterior air because of the insulation um, design of the house. Cold indoor surfaces can cool the surrounding air enough to force vapor to condense. This often happens on single pane windows because they lack the necessary thermal insulation available in higher quality windows. Double pane windows have a layer of gas, usually argon or air, trapped between the two panes of glass and should be insulated enough to prevent the accumulation of condensation. If this type of window appears misty or foggy, it means that its seal has failed and the window no longer holds its insulation rating. A desiccant is an absorbent material designed to maintain dryness within its vicinity. A common type of desiccant is silica gel, a porous plastic used to prevent spoilage. In a window, a tightly packed assortment of silica pellets is contained inside the aluminum perimeter strip to dehumidify incoming air that is not stopped by the window seal. Although double pane windows appear to be stable, they experience a daily cycle of expansion and contraction caused by thermal pumping. The process occurs when sunlight heats the airspace between the panes and causes the gas there to heat up and pressurize. Expanding gas cannot leave the chamber between the panes and causes the glass to bulge outward during the day and contract at night to accommodate the change in pressure. This motion acts like the bellow of a forge, pumping minute amounts of air in and out of the airspace between the panes over time. The constant pressure fluctuates caused by thermal pumping will stress the seal and eventually fail. Inspectors should be aware that there are companies that claim to be able to repair misty windows through a process known as defogging. I don't think that's an effective way. Um, Damage can appear in the following two ways. Riverbedding, condensed vapor between the glass panes will form droplets that run down the length of the window. Water that descends in this fashion has the tendency to follow narrow paths and carve grooves into the glass surface. These grooves are formed in a process similar to a canyon formation. Silica haze, one of the silica gels has been saturated. It will be eroded by passing air currents and accumulate as white snowflakes on the window surface. It is believed that if this damage is present, the window must be replaced. In general, each pane of glazing located in specific hazardous locations, right? Safety glazing type. The safety glazing must have a manufacturer designation or label that is visible, permanent, and identifies the type of glass. Safety glass or safety glazing is a stronger, safer version of ordinary glass. It is often used in locations where humans harm due to a breakage is likely, such as in vehicles and any windows that are low to the ground. Safety glass is manufactured in two forms. Laminated safety glass is typically found in windshields. It's produced by bonding of a resin or a thin transparent plastic film known as BVP between multiple sheets of glass. Tempered safety glass fractures parallel to its edges rather than perpendicular, and when it shatters, it breaks into small, rounded, general safe pieces. It is created by heating glass to a high temperature and then rapidly cooling it to produce compression stress fracts on the surface while retaining tension in the center. Tempered safety glass is commonly found in rear and side windows of vehicles, computer monitors, storm doors. Unlike laminated safety glass, it cannot be custom cut once it is formed. Laminated glass may sometimes be found in shower enclosures, but is generally uncommon in homes. Tempered glass appears more often and can be found in storm doors, skylights, sliding glass doors, and unsafe locations. Laminated safety glass is often labeled, although codes do not require it to be. An easy way to tell if an unlabeled glass is laminated is by examining the reflection of your hand or some other object. As there are two pieces of glass, you should see two different images, but you must be careful not to confuse them with the inner and outer surface of a single sheet of ordinary glass. Laminated glass is also slightly thicker than ordinary glass, although this difference is difficult to discern without the aid of very precise measurements. Tempered glass can also be identified through polarizing glasses. When viewed from an angle, black lines as a result of the heating and cooling process should be appeared um, as you approach the glass's side from an angle from the glass surfaces as it increases. When uncertain, property inspectors should always assume that glass is not safety glass. Glass blocks are not considered glazing. Glass blocks are masonry units, just like brick, tile, stone, or concrete block. Glass blocks are non-load-bearing masonry units made of glass bonded by mortar. Glass masonry units are unique because they are permitted for use only in non-load-bearing conditions. Glass blocks may be either solid or hollow. Standard or thin, they are installed with mortar. The thin ones are at least 3 1/8 inches for hollow units and at least 3 inches for solid units. And the standard ones are at least 3 inches by 7/8. All right, a door. Doors are movable barriers used to cover an opening. All right. Types of doors. You obviously have your Dutch door, your saloon doors. A blind door is one designed to blend with the adjacent wall finish. A French door has windows. A louver door has a mix of movable wooden fins. A flush door is completely smooth. Molded doors, bifold doors, sliding doors, all the good stuff. So, most doors are hinged along one side. The door swings or pivots away from the opening in one direction. A swinging door has hinges that allow it to swing either outward or inward. Typical French doors have two swinging door panels that swing in or out. Sliding doors move along a horizontal track from the bottom to top, and they're mostly sliders are commonly found at the door in the rear of the house that leads to the patios. That's where we mostly see them. Exterior doors are typically panel doors or molded doors that appear to be panel doors, also called stile or rail doors. Stiles are vertical boards that run the full length of the door and compose its right and left edges. The hinges are mounted to the right, to the fixed side, known as the hinge hanging stile, and the handle lock, bolt, or action are located on the swinging side. Garage door opener checklist. All right, so when you guys are taking a look at your garage doors, you want to make sure that you're taking a look at all your doors, make sure there's no damage to them before you open them. Make sure that you have a manual release. Begin inside the door. Have the door closed. Check for the manual release handle, a means of manually detaching the door from a door opener. The handle should be colored red so it can be easily seen, and the handle should be accessible no more than 6 feet from the garage floor. The door panels, right? From inside the garage with the fully door closed, check the panels for any damage, check all the pins, um, the springs, the torsion bars, make sure that there's no damage to any of that. The garage door should have warning labels on it, a spring warning label, general warning label. You want to take a look at that. Springs and hardware, make sure that there's no springs that are damaged or that have any issues with it. Door operation, right? So you want to check your garage door to be open. The first thing that I always do when I take a look at a garage door that has a garage door opener is I make sure that there's not a manual garage door lock on that automatic door. Sometimes people will leave the manual lock on there, and you want to make sure that no one has ever that has slid that lock in there so that if you hit that garage door opener, you don't damage the door. Right, so you want to open the door, close the door. You can pull the manual release, disconnect it. You can try that. Make sure the door opens fine. Check the door handles. Um, Again, when the door is open, right, when you open it with the automatic opener, hit the button, let the door come up all the way. Then you hit it down. Check the photoelectric eyes. Walk over there, put your foot there, make sure that the photoelectric eyes automatically reverse your unit. Also check your photoelectric eyes, make sure that they installed at the proper heights. Okay, they shouldn't be really high, they shouldn't be really low. Same thing with your button that's on the door. You want to make sure that that button to depress for the garage door opener is at least 5 feet above the surface, the floor surface, so no small children can push that button. Standing inside the garage door, you want to check and make sure that the non-contact auto reversal, there is that way of putting the 2x4 down and letting it hit it to see if the garage door automatically reverses. You could check that. That should hit the door and go back up. InterNACHI does not recommend using your hand or any body of your body to check that auto reverse thing, and I don't either. You don't want to, obviously damage the door or hurt yourself. All right, so here's some garage door labels, all right, that are provided. So I need the safety labels, the garage door button bracket safety labels, and the springs. All right, so here's a quick video, guys, that Paige is going to go through with the stairway inspection. So I'm going to press play here, and just bear with me 1 second here.
Hi, I'm Paige Peters of NACHI TV. A stairway is one of the most hazardous areas of a home. We built these mock-up stairs to go over some advanced tips and training on how to inspect a stairway. This will far exceed the InterNACHI standards of practice. Let's start here with the handrail. Determine if the stairway should have a handrail. Any stairway with 4 or more risers should have a handrail on at least one side. Measure the handrail height. The handrail should be between 34 and 38 inches. Handrail height is measured vertically from the slope plane adjoining the tread nosing. When there is a transition from handrail to guardrail, the handrail is allowed to go higher than the maximum 38 inches. Determine if the handrail is continuous. It should be continuous for the entire flight of stairs. The handrail is measured from a point directly above the top riser to a point directly above the lowest riser of the flight. The use of a volute, starting easing, or turnout can be installed over the lowest tread. Handrail should end at a newel post or the wall. This one does not. Handrail should be 1.5 inches from the wall. Check the handrail attached to the wall. At any point in the handrail, in any direction, it should be able to hold 200 pounds. Measure the width of the stairway. It should be at least 36 inches wide. The width of the stairway is measured at all points above the handrail height and below the required headroom height. For spiral stairways, there should be a width of at least 26 inches measured at and below the handrail. Measure the handrail projection. Handrail should not project more than 4.5 inches. Measure the width of the stairway. When there's only one handrail, the width of the stairway should be at least 31.5 inches. When there's 2 handrails, the minimum width should be at least 27 inches. Any projection below the handrail that is less than 4.5 inches, such as treads or stone, is permitted. Let's measure the risers and tread runs. The riser height should not exceed 7 3/4 inches. For spiral stairs, the maximum rise should not be more than 9.5 inches. The greatest riser height should not exceed the littlest riser height by more than 3/8 of an inch. Make sure that the riser height is at least 4 inches and the tread depth is at least 10 inches. For spiral stairs, all treads should be identical, and each tread should have at least a 7.5-inch tread depth at 12 inches from the narrower edge. For winder stairs, treads should have at least a tread depth of 10 inches measured at a point 12 inches from the side where the treads are narrower. Winder treads should have a tread depth of at least 6 inches at any point. Let's measure the difference between tread depths. The difference between the greatest and the smallest tread depth should not exceed 3/8 of an inch. For winders, this is measured at the 12-inch walk line. Let's check the slope. The walking surface should not be steeper than a 2% slope. On stairways with solid risers, there should be a nosing from 3/4 of an inch to 1 1/4 inches. The radius of a nosing curve should be no greater than 9/16 of an inch. A nosing is not required when the tread depth is at least 11 inches. So let's check the guards. A guard should be able to hold a 200-pound load in any direction along the handrail. Measure the elevated floor level. Any floor level that's higher than 30 inches above the floor below needs a guardrail. Next, measure the guardrail. The height from the elevated floor to the guardrail should be at least 36 inches. Measure the total rise of the stairway. Any stairway that has a rise of more than 30 inches needs to be accompanied by a guardrail of 34 inches or greater. The spindles need to be able to withstand a horizontal load of at least 50 pounds. Guards should not have an ornamental or horizontal pattern that would create a ladder effect for children. Next, I'll be using these spheres to help me determine the width between the spindles. Spindles on any open stairways between guards of elevated floors and on balconies and porches should not let a 4-inch sphere pass between them. An open riser should not let a 4-inch sphere pass through unless the total rise is less than 30 inches. The triangular area caused by the rise, the tread, and the guard should not allow a 6-inch sphere to pass through. Guards on the sides of stair treads should not allow a 4 3/8-inch sphere to pass through. Inspect the hand grip. The hand grip can be a 2-inch circular hand grip or a non-circular hand grip. A circular hand grip has a cross-section minimum of 1 1/4 inches and a maximum of 2 inches. A non-circular hand grip with a perimeter minimum of 4 inches and a maximum of 6 1/4 inches should have a maximum cross-section of 2 1/4 inches. A non-circular hand grip with a perimeter greater than 6 1/4 inches should have a graspable finger recess on both sides. All handrails should be equivalent to the 2-inch circular grasp. One should be able to consistently grasp the handrail without needing to release or twist their fingers. Inspect the headroom. The headroom should be at least 6 feet 8 inches, and in a spiral staircase, the headroom should be 6 foot 6 inches. Below the stairs, enclosed accessible space should be protected with 1/2-inch drywall. At the bottom of the stairs, inspect for mold, water damage, and insect infestation. Inspect the landings. There should be a landing at the top and bottom of each stairway. There is an exception to this rule, though, provided that there is not a door that swings out over the stairs. Inspect the total rise of the stairway. A stairway should not have a total rise of greater than 12 feet. The landing should be at least 36 inches in width, measured in the direction of travel. Let's check the lighting at the stairs. All stairs should have a means to illuminate the stairway, including treads and landings. In addition to this, each landing should have its own light unless there is a light installed directly above the stairway. Check for controls. Interior stairways with at least 6 risers require wall switches at each floor level, unless the lights are continuously illuminated or automatically controlled. Exterior stairways should have a light located at the top of the stairway. Exterior stairways from the outside ground level to a basement should have a light at the bottom of the stairway. Lights at an exterior stairway should be controlled from the inside of the property. Well, I hope we've given you some helpful hints on inspecting a stairway. Thanks for joining us at InterNACHI TV, and we'll...
All right. So doors, egress, and landing. Regardless of the size of the house, at least one egress door should be provided. The required door should provide access from the habitable area of the home to the outside without going through a garage. The required door must be a side hinge door, and it must provide a clear space of at least 32 inches wide, measured from the door surface to the door stop. All egress doors should be readily openable from the inside without the use of a tool, key, or special knowledge. The width of a landing should not be less than the door's width. The minimum dimension of every landing is 36 inches, measured in the direction of travel. On each side of each exterior door, there should be a floor or a landing. The floor or landing should not be more than 1.5 inches below the top of the threshold. There are 3 exceptions. If the door does not swing over the landing, then the exterior landing can be at most 7.75 inches below the top of the threshold. This is applicable to all exterior doors, including the required egress door. If a stairway with at most 2 risers is at the exterior side of a door, other than the required egress door, a landing on the outside is not required, provided the door does not swing over the stairway. Again, the screen or storm door is allowed to swing over the stairway. A floor at all exterior doors, other than the required egress door, should be no more than 7.75 inches lower than the top of the threshold. It is also acceptable to raise the threshold of an exterior door, other than the egress door, up to 7.75 above the floor. Hallways and ramps. The minimum width of a hallway is at least 36 inches. There are 3 main points to check while inspecting a ramp. They are slope, landing, and handrails. Ramps should not have a slope greater than 1 unit vertical in 12 inches horizontal, or an 8.3% slope. A minimum 3 by 3 foot landing should be installed in the following 4 locations: at the top of the ramp, at the bottom of the ramp, where doors open onto the ramp, and where the ramp changes in a direction. Check the handrails. There should be a handrail on at least one side of all ramps that have a slope greater than 1/12 slope maximum. Most installers typically install a handrail on all ramps regardless of the slope. Check the handrail's height. The height of the handrail is measured from the finished surface of the ramp, the minimum 34 inches. Check for continuity, right? The handrail should be continuous. They should terminate at a newel post or safely terminate. Measure the space between the handrail and the wall should be at least 1.5 inches, and the length, the maximum rise of any run shall be 30 inches. Stairways, okay. Stairways are almost most hazardous as the home, as you saw in the video. You want to measure the stair rail height, right? Check to make sure the stair rail handrail is continuous. We want to check the termination point, the clearance, the attachment to the wall, the width of the stairways. You also want to measure the width of the balusters, right? The handrails and risers and treads, the nosing. We want to check all that. That was a great video that we watched. that had all that. And if there's any variations in that, the slope of the treads, if there's any obviously damage to them, you want to walk up down, make sure that they are secured and not sagging or loose. And then obviously, make sure that they're safe to walk on. Handrail height and code. Uh, I'm gonna just pass that video, guys. Um, but this is handrail height and code. So inspect the guards, right? Guards should be constructed so as to prevent adults from falling over them and children from crawling through them. The height of a guard is measured vertically from the sloped plane adjoining the tread nosing or leading edge. You want to check the guard strength for up to 200 pounds. Check the strength of the rails and all the balusters. You also want to make sure to measure them, that there's no ball 4 inches cannot pass through them. You want to measure the height of the guardrail. The minimum height of horizontal guardrails are 36 inches, open sides of stairways with a total rise of more than 30 inches above the floor. Check for any damage, check the ladder effect. Guards should not have horizontal or ornamental patterns, members, attachments, or openings that would facilitate any climbing on those railings. You want to notate those in your reports. For glass railings or glass guards, uh, glass used as a handrail assembly or a guard section should be constructed of a single fully tempered glass, laminated fully tempered glass, or laminated heat strength glass. The minimal thickness should be 1/4 inch, and each pane of safety glazing installed shall be identified by a manufacturer's designation, which shall be etched or sandblasted or ceramic file laser etched into the glass. And that shouldn't be removable. All right, guard openings shouldn't be more than 4 inches, right, to pass through. Open risers should not allow the passage of a 4 inch spear on stairs with a total riser of 30 inches. The triangular area formed by the tread shouldn't pass a bigger than a 6 inch diameter, and the opening at guards on the sides of stair treads should not allow for more than 4 3/8. Hand grips. Okay, so you want to obviously inspect the hand grip. It should be a continuous hand grip that starts from the bottom of the stairs to the top. And it should be obviously graspable. A circular hand grip should have a cross section of a 1 1/4 inches and a maximum of 2 inches. All handrails should be equivalently graspable to the 2 inch circular hand grip. A circular hand grip should have a cross section of 30 meters or 43 meters for you in Canada's. Inspect the non-circular hand grips. Okay, so they should have a cross section of no more than 2 1/4 inches, right? And they should be hung off the wall and be secured to the wall. You want to test that as well. Um, the headroom for stairs. So headroom is measured vertically from the sloped plane adjoining the tread nosing or from the floor surface of the landing or platform to the obviously the ceiling height. The headroom in all parts of a stairway should not be less than 6 feet 8 inches. Spiral stairway should have headroom of at least 6 foot 6 inches. All right. An enclosed and accessible space under stairs should also be protected on the enclosed side with a 1/2 inch gypsum board. All right, landings, illumination, and attachments. So you obviously want to make sure that all your landings and your attachments of any of your guardrails are all secured. All right. You want to inspect them. Every landing should be at least 36 inches in the direction of travel. All right. Exterior stairways should be lit. Interior stairways should have switches if they're more than 6 risers on both sides, so top and bottom. It should be a three-way. All right. And then if you have a basement stairs, you want to make sure that you have a light at the bottom of those stairs. Emergency escape and rescue openings. So, An emergency egress is an exterior window, egress door, or a similar component that can serve as a means of escaping in the event of an emergency. Basements in every sleeping room should have at least one emergency escape and rescue opening. Such openings should open directly onto a public street, public alley, yard, or court. Um, you want to check your sleeping areas or basements where it contain one or more sleeping rooms. These openings should be installed in each sleeping room, but are not required to adjoining areas of the basement. Basements used for mechanical equipment only and not larger than 200 square feet do not need to have an emergency exit area. You want to measure the sill height of the window, and it should be not more than 44 inches above the finished floor. The opening is required to be a minimum of 5.7 square feet, and the height and the width of the window should be a height of 24 inches and an opening of 20. You want to check the window's operability. You want to make sure they can fully open without the use of a tool, a key, or any special knowledge. You should be able to operate it out without asking anybody. And the horizontal area of that window well should be at least 9 square feet. So if it's below grade, it should be and project 36 inches out so that you can easily exit that area. There also should be a ladder or some kind of step so that you can easily walk out. Wells with a vertical depth of at least 44 inches should have a permanent ladder or step with inside width of 12-inch maximum at least 3 inches from the wall and should be spaced no greater than 18 inches apart. Bulkhead should open to a fully open position as they should meet minimum net clear opening requirements. You want to check covers for all windows, right? For below grade windows, they should have bars, a grill, or a cover, some kind of screen to prevent somebody from actually falling in them. And they should be easily accessible to push open and get out if need be. They shouldn't have a lock on them or a chain or some kind of bracket securing them. Emergency escapes and rescue openings are not allowed to be under decks and under porches, providing that the opening can still be fully opened from underneath. Floors, walls, and ceilings. So throughout your house, you want to obviously be checking all of your general conditions. All right, floors are designed as walk-in surfaces. Floors all should be level. Water damage is one of the major conditions to look for when inspecting the interior. Water damage can often be found around areas where there is water, such as the toilet or sink, or any bathrooms, appliances in the kitchen as well. If you're not able to determine the material the floor is made of, you could find a floor register, right, and pull one of those up and look. You never want to pull any or peel up anything or take anything apart, but that's the easiest thing to pop up is like a floor register. There are many things to look for in relationship to inspecting the floors, trip hazards, water damage, any damage, cracked tiles or loose grout, any wet areas, any heaving or sloped areas, any wood rot, buckled boards, squeaks, stained carpets. For walls, you're going to look obviously to make sure their general overall conditions in good shape. Could be plaster, drywall, wood boards, paneling, etc. There are many things to look for in relation to inspecting them, right? Wood damage, cracking, nail pops, bulging, any thermal bridging, wood rot, ghosting's a big one. If you see black lines that look like all the joists. So that's something you guys can note. The ceiling materials are similar to the walls. All right. Uh, and then here is a video for the interior inspection, but I don't know if we have enough time for that, but I'll click it and we'll.
A representative number of doors and windows by opening and closing them, the floors, walls, and ceilings, the stairs, steps, landings, and stairways and ramps, the railings, the guards, the handrails, and the garage vehicle door and the operation of the vehicle door openers using the normal operating controls. And then the inspector must describe in the report a garage vehicle door as manually operated or operated with a garage door opener. And then the inspector shall report as in need of correction any improper spacing between intermediate balusters, spindles, and rails for steps and stairways and guards and railings, the photoelectric eyes, the safety sensors, anything that didn't operate with those, and any window in the house that had obvious fogging or lost seals or damage or cracked window panes.
You know, the first thing I start out doing is I document the home when we get there. I take time-stamped pictures of each room, actually the exterior also. But we'll go through and take pictures of each room. That way we have documentation of the condition of the house when we first started. With that, we'll start. You know, I'm taking pictures mainly to document the condition of the house. You know, we'll document all areas of the house, which I've already gone through and done majority of them. You know, we'll go to the kitchen and start checking the receptacles. We actually start checking the stove first, turn it on and make sure it all lights and functions properly. Once we get all burners lit, we'll take a picture and document it and say it's a functional stove. If not, we'll document what is wrong with it. There's nothing wrong with this one. We'll check the drawers, cabinets, just to make sure they work. You know, one of the things that we've noticed on this stove is on the griddle, you know, there's a grease trap underneath it, but it dumps the grease into the drawer below. So we'll document that in the report. And like I said earlier, we make sure all the gas valves are off, check all the drawers, cabinets, make sure they function. Look for dishwashers. We've already started the dishwasher in previous. Check the cabinet drawers, doors. Check the windows. Make sure they are functioning properly. This one does. We'll turn the water on in the kitchen sink. Make sure the hot water and cold water are oriented correctly. If the hot water is forward, it'd be a child safety issue. So we make sure that we'll document that. We'll plug the drain and fill the sink partially full of water. Check the drain underneath just by feeling the P-trap and stuff to make sure it's not dripping or leaking. We also document the amount of stuff in underneath the sinks, just so we can, you know, document what is there. Just to make sure it is functioning properly. Check the high loop on the dishwasher. Then we start checking all the receptacles. Now, I tripped these earlier. We will always note where the reset is for the kitchen.
All right, guys, that video is pretty long. That goes over, obviously inspecting the entire interior of the house. All right, but you can definitely check that out at InterNACHI if you would like. But we'll finish up here. So there's another video inspection of the kitchen area that Ben will go through. And again, you guys can definitely take a look at that at InterNACHI.org. All right. So the last thing we'll kind of quickly go over is the inspecting for the utility room. So what to look for in the utility room. Right, the water heater you want to look at, make sure it's free and clear and not damaged. You want to make sure there's no water leakage or any moisture issues. The furnace, the same thing. You want to take overall condition of that. Check for all the penetrations around the fuel lines, all the duct work. You want to make sure that there's no spot for any moisture or air leakage through those units. You want to make sure that it has a ventilation properly. All right. Make sure that there's a dehumidifier or a humidifier. Make sure that there's no condensate lines that are clogged or plugged, and that all of that is in good working order. For your tips for utility rooms, right? Carbon monoxide detectors, one way to help early detection for any issues. You want to make sure to install those. Your clients will save money on their utility bills if the heat exchanger and cooling coils, their air conditioning and heat pumps are clean and dust free. Air filters, keep all your ductwork sealed and taped. Any drains, you want to make sure they're free and clear. Check your roof, your gutters periodically. You know, and then, you know, a lot of people don't inspect their attics and crawl spaces annually, but it should be something that they should be taking a look at and checking. So you definitely want to mention that to clients. A lot of people don't go in them, right? Check it and looking for your insulation, your ventilation, making sure that it's not cold or hot when it's not supposed to be. So it's important with your, you know, keeping your house running and most efficiently and effectively as needed. As always, you guys can check us out, nachi.org, for any helpful hints and tips that you need. Appreciate everybody joining me on this Wednesday and AJ. And, you know, here's all my information if you have any questions, concerns, or just want to chat and check in. So I appreciate everybody's time. Thank you guys.